many attempts to use robotics in the nuclear decommissioning failed. So we know that exploration is important for our time, but we have to think also on the future for future generation. We need to think that also they will to take care of it. So I think RAS, the Robotic and Automation Society, can be do more, and robotics can be of great help. So if we talk about the environment, so like if we think about a robot that has to manipulate some object in the glove box or have to do inspection, we can also see a lot of problems that can arise from this type of task. For instance, we know that it's very hard for a robot to manipulate an object as we do. But if we consider other tasks like exploration and navigation in environment that are very different, we know that in Fukushima, we are for instance, we have very different situation in the different units, and we have water, and there is a radiation that is really affecting the camera. So it's not so easy as we want to navigate in a human-like environment. So it's a very challenging problem. And for this reason, we are here today, and the aim of this workshop are mainly to understand the challenge that are needed to be solved, and to learn, from others. I think there are some people here in the workshop that are also new to robotics and to nuclear robotics, and are applying some technique to this field. So I think it's very important. And of course, it is important to networking and exchange ideas. So please use the coffee break to talk and exchange, communicate. And I think it's very important that, and we are grateful that now we have again this possibility. And as I said, we want to promote more research effort. And I have to thank all the organizers, my co-organizer of this workshop. We are a big team, and it's my lab from the University of Tokyo and the University of Sussex, and we are challenging this problem. We are working in a new mechanical actuator robot manipulator, but there are two of the co-organizers that will give a talk, so you will know more about our work during the workshop. And this is the program. So we will have a morning session, and in the morning session we will have different talk. In this workshop we have 8 talk from speakers that are known for their work in nuclear decommissioning, but as I said, also new in this application. And we had 8 contribution, and I would to say that all the papers were really nice, and we were very happy with receiving all this paper. Like we select 8 from the contribution we got, and all of these 8 are nice. So please, especially for people that are experts, look on this paper and give suggestion to this new students that are working on the field. And from this paper, it was really difficult, but we select 3 best contribution, and we have 3 finalists, and there will be at the end of the workshop best paper award. The workshop is endorsed by the Technical Committee for Robotics and Automation in Nuclear Facility. And if you work in this area, please consider to join them. I know they are looking for I think a new chair, and also if you are young, you can be a junior co-chair and learn from them. So get in touch with the chair of this committee. I think it's nice if you really want to help the community and get more sensibilized about nuclear decommissioning, to join this technical committee. And yeah, this is the end of the introduction. And actually, the first speaker is Rich Walker for the Shadow Robot Company that is based in UK. And actually, he cannot be here, and he couldn't join even online because of time zone problems. So for him, we will play a video, and there should be here. So he will answer the question. And the Shadow Robotics company is one of the best company in robotics in the UK. So like they work a lot with manipulation, and now they are also tracking some problem related to the commissioning. And they have a booth here in IROS. So please go and talk with them. And yeah.
Good morning, ladies and gentlemen, and thank you very much for taking the time to listen to this little talk today. I'm Rich Walker, Managing Director of the Shadow Robot Company. This is Pirate. He's joining me to help me stay on track with my talk. I'm going to run through a little bit about what Shadow have been looking at in terms of robotics for nuclear, particularly telerobotics and advanced technologies for that. So Shadow are a leading technology developer. Many of you will know us for our work in dexterous robotics. We've been making, we believe, the most advanced robot hands available in the world for well over 20 years now. And these have gone primarily to people in the R&D technology space. We like to make it possible for our customers to push the boundary of what's been done before to advanced dexterity, fundamentally, and to be able to play with our robots however they want. We provide them with absolutely fantastic support in doing that, in letting it possible for them to do what it is they want to do, and hopefully have fun doing it. Play, support, fun. That's our kind of key mantra there. So the Shadow teleoperation system is built on the Shadow hand. It then integrates into that some universal robot arms, which we like because they're very friendly, human compatible arms. And then a motion tracking system. The illustration here shows the Shadow gloves we've been developing, which have sub-millimeter fingertip tracking accuracy. The movement of the hand and arm is very wide-ranging. It's very fluid. It's very dexterous. When you're wearing the system, you have the ability to make the wide movements that a human can do, and you can exploit the fact that the robot arm has bigger movements than you by using a mechanism we refer to as clutching. The same way you move a mouse across the desk, a short distance to move the pointer across a much larger screen. The robot hand is hopefully as capable as we can get it, as close to your hand, and we think that this system offers a really good step forward in what can be done in terms of teleoperation for remote dexterity. We have two versions of the system because the jury is still out on one of the fundamental questions about teleoperation. And that fundamental question is, when and how do you need a sense of touch? And this to us is a really, really interesting problem. On the left, you can see there the non-touch system, which is a Shadow glove. That's basically a wireless motion tracking system that gives you very, very precise fingertip movement with no occlusion, no interference. So it's possible to make the very small movements needed to roll a pen in your fingers or handle a wire. On the right, you can see the current Haptex DK1 glove. This is a very, very powerful haptic feedback system. It gives you an incredibly good sense of touch, incredibly immersive, but as you can see, it does take quite a lot of space around the fingers. I believe there's a new version of the haptic system coming out now, but this is the system we've been working with. Obviously, if you're using the Haptex glove, then you require fingertip touch on the robot. Something like the Biotax we found to be very good for doing that. So the Shadow dexterous hand is designed to be as close as possible to the human hand in a robotic form. We have 24 movements, 20 degrees of freedom, positioning the fingers and the knuckles to give you pretty much the same range of movement and kinematic space as the hand. Side-to-side movements of the fingers, 129 different sensors enabling us to measure position, force, touch, and so on. 2 degrees of freedom at the wrist. All the motors are integrated into the forearm, and even a palm curl so the little finger can come up to oppose the thumb. So we've gone as far as we can go here, current state of the art, to building a human-like robot hand. So the video here will show you some of the capabilities of the system. You see Joanna here, one of our experienced operators. She's using the Shadow gloves, and this is just showing you the range of movement of the hand. Those are non-tactile fingertips. They do have a touch sensor, but it's not the Biotac. You see there the wrist movement, and there the fluidity of this motion. This is very easy to wear. The glove doesn't really interfere with your hands very much. It's quite comfortable and lightweight to wear, and yet it gives you this kind of wide range of movement ability. So what does the haptic feedback do for us? Well, you see here a configuration where on the right, we're mapping out how the haptic system works. We have the SynTouch sensors to measure the fingertip. We render those to the haptics glove so the human can sense it, and then the human can provide the intelligence that drives back for the actuation. And this has allowed us to build a tele-robot system that we can operate over long distances. We've done it from London to California over a 4G phone connection, which was quite spectacular. On the left, you can see, actually, that's Mike, the R&D director from Haptex, wearing a blindfold. That's not a VR headset, very important point. He's wearing a blindfold, and he moves his hand across the table until he feels the ball, and then when he senses the contact, he goes, right, now I close my hand on it to pick it up. So that's what you can do, particularly with a sense of touch, operate without line of sight. But do you always need a sense of touch? That's one of the deep questions we want to understand about grasping. Obviously, there are challenges that are worth pursuing in robotics technology, and one we think is Jenga as a service. So we've been spending a lot of time exploring how exactly robots can do Jenga with humans controlling them, and can we make that as much fun as it is to play Jenga live. I can tell you right now that when it crashes, it still makes exactly as much noise when a robot does it as when a human does it. But you can see there that Mike is quite capable of operating the robot to take the Jenga brick out and put it on top of the stack. So what are the current challenges to touch? The first is that it's really hard to understand what the objects are that you're engaged with. We have various different characteristics that we want to understand about the objects. What's the temperature of them? How hard are they? What do they feel like when you move your fingers across them? What's the shape of them? How big are they? And also, how heavy are they? And all of these are things that humans get through touch. Of course, robots without a sense of touch are, we know, not very dexterous, not very graceful. This is a classic teleoperated robot destroying things because it doesn't have that feedback necessary, that sense of touch to understand the world. What we've seen with people working with prosthetics is that they use vision to compensate for the lack of touch. If you watch someone using a prosthetic hand, you'll notice that they stare a lot at the objects they're interacting with, precisely because they're using their vision instead. But that means they're using concentration and attention, and that's costly for a human. So we have some fairly fundamental research challenges that we'd like to throw open to the audience. All of these we can talk about some more, and if you come along and see our system over in the exhibition area, we can talk to you in more detail about these. But really, we want to be able to build robots with skin that is as good as human skin in some way, shape, or forms in terms of that sense of touch. And then we want to render that back to a human in a way that they can interpret it and understand it. So gloves that have the similar actuation capability as the skin makes possible. We care a lot about video. We care a lot about seeing what's going on. The resolution and performance of depth cameras is not that good yet. Having that work well, or do that, whether that's done directly or through clever image processing at video speed, will be a real game changer. Tracking the precise motion of the human hand is still not all there. We are working with some very nice data gloves, but that technology could always be pushed forward, we think. One key challenge is, how do you train someone to use a system like this? We've noticed that if we start you off with the 2-year-old's wooden blocks, you find it easier to then do a more difficult task. And if you start straight up with a difficult task, what's an optimal training sequence for getting someone up to speed? And how do you see what's going on at the remote location? If you're operating this, how do you get the sense of view that you would have if you were there? And how do I get the ability to move my head around in the virtual space and see what's actually happening in the real physical space? All of these we think are interesting challenges that you can explore with teleoperation now. Obviously, if you control the environment, you can make a robot that's very, very performative. The MIT Rubik's Cube solver is incredibly fast precisely because there is no variability. But dexterity is about responding to the unexpected. So in a fully defined environment, you can build a machine that will do something perfectly and it will work incredibly well. But as soon as you have something that's uncertain, you need vision to plan, and then you need touch to handle that uncertainty. So where are we trying to go with this? Well, we think that once we start building in vision and touch and dexterity, and we build these teleoperation systems with them, we can put your hands anywhere. This could be transporting skills to a distant location, repairing a piece of machinery off-site. This could be using it for machine learning, teaching a robot how to perform a task by having a human do the task using the robot. This could just be, of course, and this is what we're all here to talk about, putting this in dangerous or inaccessible environments. And lastly, and most interestingly in some ways, is using it to get semi-autonomy. Imagine you have multiple robots, but only one operator, and the operator can switch from robot to robot when the robot is ready for the human skill to be there. So that could be a real game changer in terms of scaling up a task. So why do we think touch is important? Well, it's because it doesn't make the impossible possible, but what it does do is it makes things that are difficult intuitive. As soon as you can use your sense of touch to engage with the object, to engage with the world, then you can relax part of your brain that's concentrating on the task and get on with it. And that's really, really powerful. So how do we see this working in nuclear? Well, the system on the right is your classic billionaire playing with an expensive toy. But this is actually not that expensive a toy when you compare it to the cost of running people on site in full PPE. You can put those robot arms through a glove port, have them inside the working space, and then have the operator remotely. They might be very close, they might be a long way away. And the ability to have the sense of touch and the ability to understand the world at the remote location means that a skilled operator can do the tasks they would do today quicker, cheaper, and safer. So this is kind of our concept, move from the picture on the left to the picture on the right. Obviously, sweeping up lentils is not that challenging a task for us, but that is obviously difficult if that is metal swarf in the bottom of a glove box, or if this is a spill that you need to mop up inside a controlled chamber, or dust you need to clear up. You can see there, though, it's very easy for the operator to perform that task. So in terms of the particular gains for nuclear, we can look at eliminating dose exposure. We can look at enhanced safety and productivity, because the robot hands can be used for more hours operationally than a human who needs to suit up and go in and out of a controlled area. We can get rid of the need for people to wear those suits, that PPE, because they're staying out of those areas. That's kind of important, because the ergonomics of PPE is very bad. If you're wearing an air-breathing suit and trying to do more than a couple of hours of work a day, it's not going to happen. And finally, the robot, because that's doing the work, reduces the overall amounts of secondary waste produced. You're not generating that endless stream of PPE that has to be managed and disposed of. So we think there's some really interesting fundamental advantages to using this sort of technology to address challenges where today you're putting people's hands into nuclear environments to do skilled tasks. So unfortunately, I'm remote and I'm pre-recorded, so I can't answer any questions. My colleague Juan Laforgia is in the audience there. Juan, give us a wave. Thank you very much, Juan. And Juan will be able to take any questions now. He understands the system, and also we have the system over in the exhibition area, and Juan can arrange for you to come and try it and understand for yourself exactly what this kind of dexterity can and can't do. So thank you very much. Have a great workshop and an excellent IROS. It's my pleasure.
Our next speaker is Professor Glovnea from the University of Sussex. He's the head of the Department of Engineering and Design and head of the Robotic and Mechatronic System Research Group. And I think for him is your...
Morning, everyone. You hear me without a microphone. I'm Alexis for over 36 years, so I can speak very loud. Yes, I'm not a roboticist. My research area is in biology, mechanical design, machine component design. So you will wonder what this guy is doing here. Well, I'm not completely lost, although they didn't find my name at the registration, but I'm not completely lost. In this field, I do mechanical design using a device, a toroidal type CVT, as an actuator, a variable impedance actuator. You'll move. Excellent. Thank you very much, Andrea. So, yeah, I can start now. Good morning, good afternoon, and good evening for wherever in the world you are. Yeah, this still doesn't work, so I leave it there. I will talk to you about after a short introduction, but please bear with me, because I see in robotics, I just noticed in robotics conference a lot of very nice presentation, flashy images, very cute animations. I don't have something like that in my presentation. it's more, as I said, mechanical design. And you like it or not, you'll have to accept it with my sincere apologies. So I'll talk after introduction a little bit about variable impedance actuators, just a few words. Then I'll present a few words about continuously variable transmissions in robotics. Then I'll talk about the specific type of CVT, which we call it constant power CVT, and I'll explain why that, and then a few conclusions. Thank you, Angela. So obviously, as I only heard recently, interaction between robots and humans, but also robots and environment require collision-safe capabilities. And we saw in the previous presentation how that hand can pick up very fragile objects. So, yes, I think I can do it, honestly. Thank you very much. I don't need it. So, so obviously, to achieve that, we need actuators with a variable impedance, which also, as you definitely know, is called variable stiffness capabilities, in order to make the robot, the manipulator, adaptable to the surrounding. So for this reason, extensive research I found that has been carried out in the field of robotics in recent years. And variable impedance obviously can be achieved in many ways, that you very well know, with control with mechanical or electromechanical means, or a combination of these. Obviously, control only, if it's possible, means a lot of sophisticated sensors. Also, in relatively recently, variable impedance, continuously variable transmissions, or CVTs, have been tried in various robotics structures, let's say, at various joints. Well, and that's exactly what we are trying to do here. Why is that? Is because we think that in nuclear environments with very strong radiation, sensors make variable electronic sensors and other electronics may have serious problems operating. So what we try here is to achieve safe collision with mechanical means only, without any electronic sensor, or with a minimum electronics, just which we know is safe and is not affected by the strong radiations. So very briefly about continuously variable transmissions. As you may know, they are just some gearboxes which are able to shift between gear ratios seamlessly, continuously. We can say with an infinite number of gear ratios between a certain given range of values. So, what does that mean is that the input of the CVT it can be kept at a certain constant speed, angular velocity, no? While the output speed can vary, as I say, in an infinite number of ratios. And CVTs are quite old. Maybe one of the greatest minds of all time, Leonardo da Vinci, also showed us the first schematic of a CVT, although the first patent in Europe was patented in the 19th century. And CVTs have flourished, if you want, in an area due to especially the automotive industry. But they're not used only in the automotive industry, and they come in a great variety of shapes, designs, as you see here. Maybe the one on the top left, also called the COP variators, is very well known nowadays. An American company use it for push bikes, for example. Then the second on the left, the toroidal, which is mainly used in for some models in the automotive industry. And the third on the left, the bottom, the chain or belt and pulleys is also widely used in automotive industry. Obviously, a vehicle equipped with a CVT will be able to allow the engine to run at the most efficient point. Of course, we now get rid of internal combustion engines, at least for the moment. So it means that CVTs find their ways in other areas. And we try to find a way to use CVT, the toroidal CVT, in robotic applications. As I say, it can be used in, it is used actually in food and pharmaceutical industry, textile industry, in automotive industry, and for example, also in power instrument drives, as found in older computers, but any computers which have a disk drive. The most widely used CVTs are very simple in their design, and it's called the V-belt and pulleys. Obviously, it has two pulleys, as you see here, which can adjust the distance between them, an input and an output, and in between a belt, a flexible belt. This is a special construction, as you see here, where, with various blocks, a number of blocks on a flexible steel core, which means is able to transmit quite large forces through friction. We call it boundary in ecology, which means a very, very thin lubricant film, molecular level, I would say, which doesn't have much of reducing friction or even dry friction. So by changing the distance between the disc, obviously the radius of contact between the belt and the disc changes, so the transmission ratio changes. The other very common type is the one called toroidal CVT. This was made very popular by some Japanese car manufacturers like Nissan, which used this type of CVT in some of their models, and Toyota as well. Actually, I have a little Lexus equipped with a CVT. So obviously, two input drives, which have a toroidal shape, and a number of power rollers in between. By changing the angle of rotation, as you see here, of the rollers, we can change again the radius of contact between the input and output discs, thus transmission ratios. And in this case, the power is not transmitted through dry friction or boundary friction, but through the shearing of a lubricant film. This is why we call it also traction force instead of a friction force. from the analogy with the traction between the locomotive wheel and the rail, which obviously is the one, that force is the one pulling or pushing the locomotive forward. This type of design, the toroidal CVT, can be either full toroidal, as you see here, so the very simple schematic, the input and output discs are toroidal, full toroidal, while the rollers obviously also have a toroidal shape, and half toroidal, like this. Actually, the Nissan toroidals are CVTs are half toroidal, and yeah, yet again by rotating the position, changing the position of the roller, the radius of contact change, which means variable velocity at the output, even though the input is kept constant. Now, continuously variable transmission sometimes is also called in mechanical transmissions an infinite variable transmission, when we can achieve at the output a neutral position, which means zero speed. And if we divide the input by output, which is zero, we get an infinite value of the transmission ratio. And this is why they are called infinitely variable transmission. This is most often achieved with combining a CVT, any design you saw previously, with a planetary gear set. The use of a epicycling gear obviously will help the increase of the torque, the output, also overall efficiency of the device. Now, I don't know how much efficiency is important in robotics, maybe not much, but in my area of mechanical transmission, efficiency is very, very important. So in this project, we try to explore the viability of employing a particular type of toroidal CVT as a variable impedance actuator in the as an actuator also for manipulators or robots used in nuclear decommissioning tasks. Obviously, as I said, this is a purely mechanical device, but it can achieve automatic variation of the speed only through mechanical means, and no sensors are required. What is this, call it constant power CVT is about, how it is built? We have obviously the input and output shaft, which the input shaft receives a power from a power source, normally an electrical motor, but can be anything else, and transmitted to the output shaft. And we want, obviously, variable speed at the output shaft. On the input shaft, there are two, we call it input discs. One with a conical shape like that, but can be also different. For simplicity, we keep that conical, and that will rotate with the disc, with the input shaft, but it's also fixed axially. The other disc, which is always toroidal, also obviously rotates with the input shaft, but it can move axially on the shaft with any type of machine component like splines or other. The output, which is connected to the output shaft, the output, this is also conical, but inverted conical. Here, this would be the conical surfaces. And in between these, there are a number of intermediary elements, which are just spheres. Now, the motion, obviously, and the power is transmitted from the input shaft through the two contacts between the intermediary balls, yes, and the disc, and through the contact here to the output shaft, output disk, and to the output shaft. Now, on the actually between the disk and the output element, there is also what we call a converting torque device. I call it a coupling. In the simplest form, it's just a screw. In a more sophisticated design, which we did in the past, was a little bit more sophisticated. It was a ball screw to reduce friction and increase efficiency. In this design, which we use here, is an axial clamp. But so can be any device which can convert a variation of the torque into an axial force. Obviously, at the beginning, in the initial stages, or without a significant torque at the output, we need a certain force applied to the toroidal disc in order to compress the discs and the balls together, because obviously without a normal force there is no friction force according to Coulomb and Amonton's law. So how this device works? So as I said, initially low torque at the output. We just need a low force at the beginning and the rather low power at constant speed is transmitted. Now, when the torque at the output changes, let's say increases, as I suggested here, this coupling pushes the output disc axially. Obviously, this surfaces will force the balls radially inwards, which means the contact points between the discs and the balls will change. You see, also the axis of rotation of the ball will change, as you notice like in this drawing. And this consequence, as a consequence of this, the transmission ratio will change. So this is completely controlled by the torque at the output and not by any sensor or anything. Just increasing the torque will increase the yes, the transmission ratio, will decrease the output speed. Which means, to give an example, to take from the previous speaker, which shows us so nicely the robot handling an egg or a bone. Very similar here. If we have such a device in the actuation of a robot hand, obviously at a certain predetermined torque, the increase in the torque when the fingers start pushing on the egg, yes, that will cause a reduction of the speed of the output. And eventually, if we have a epicycling gear there at a certain speed, at a certain torque, with other words, the velocity becomes zero, and the fingers do not squeeze further the egg. So this obviously achieved fully mechanical and with no sensors at all. So this is a very simple animation. You see the input disk, the output disk, the output, and the intermediate balls. When the output disk starts moving, the contact point changes, and obviously the transmission ratio changes with that. So the main characteristics of this CVT, it offers a quite good range of ratios and I would say reasonable torque capacity. When I say range ratios, we mean we can have a transmission ratio between 0.2 and 6, even larger than that, which means a ratio range of 12, but even 20 can be achieved, which is quite good if you are familiar with mechanical transmissions. And quite compact design, and this is why we try to use it in this particular application for rather low torque. which means you just make it smaller, so it transmits the dimensions of the device are smaller, the forces applied are smaller, and also for larger tasks, if you want, for a larger payload. So this is just an example of a transmission ratio. Depending on the geometry of the dimensions of the device, of the angles of the various of the two disks, we can have, as I say, any transmission ratio between 0.2 and 6 or higher. And the variation of the transmission ratio, you can see there. The variation of the torque. And this is the power. And I call it relative power because I divided the maximum power by the actual power, which changes with the angle of contact between the input toroidal disk and the ball. You see very little variation of the power. For this reason, we call it constant power CVT. So other characteristics, obviously, I already mentioned these two: automatic adjustment of the transmission ratio. In comparison to other toroidal CVTs, or even to the belt and flexible belt and pulleys, in this case, we don't need any device to synchronize and change the axis of rotation of the element. Like the other toroidal CVTs, you see, they have axis materialized, what we call materialized axis, which means we need quite sophisticated mechanisms and control strategies to keep the axis exactly at the same position, which makes those CVTs a lot more expensive. In this case, just both without materialized axis, they will choose the axis of rotation themselves, independent of each other, which make this less prone to failure, because in the previous case, if the axes are not perfectly aligned, obviously, it may be possible that one robot transmits more power than the others, and the others are parasites, which means consumed power, which is the worst scenario. Also, it's the torque transmitted element, which means the discs and the balls are just manufactured with well-known and trusted technologies from rolling element bearings. You can buy nowadays, obviously, the balls off the shelf, no, which makes it relatively cheap. A few words about the dynamics of the CVT, but I'm not. I already explained most of it. The important things here are the angles between the horizontal and the two discs, the conical disc, and also the variable angle alpha with the point of contact between the balls and the toroidal disc. You also notice that the input velocity and out velocity are inverted. From the condition of no slip, which we can accept in this contact between the balls and the disc, we can extract through quite simple mathematics the angle of rotation of the balls and the transmission ratio. A very important element in here is the force behind the toroidal disc. So this is adjusted in such a way that at the beginning, low torque, just enough to overcome friction, let's say, whatever we have there. The angle between the contact point to the horizontal is 0. And this force is just large enough to keep the device moving and to keep the balls in dynamic equilibrium. This just shows how the dynamic equilibrium of the balls under the three contact forces and the friction forces, I call them T, traction forces, TC rather, yes, which will rotate the ball. So there is a very direct relationship between the output torque, I call it M for moment, and these forces. Further on, a change, an increase in the torque, as I mentioned, through the torque will cause a force here to push the output disk, which means that we need to change force FA in order to bring the balls back to dynamic equilibrium. Again, through very simple mathematics, we can show that there is a direct relationship actually between the output torque and this force FA applied to the input toroidal disk, which means by controlling the way this force changes, the impedance of the device can be controlled. But and in our case, in this particular project, we use a pneumatic actuation to move the position of the disk. This can be done remotely from the high radioactive area, but still it's not sensitive to radiation. So for this reason, as I said, we use this for robotic applications, but can be used obviously in other extreme environments where robustness and also collision self capabilities without sensors are needed. Apart from nuclear, we see this device working very well in space application, deep sea, and many other. So we think that this is an excellent candidate for nuclear decommissioning tasks. And actually, we've been working for half a year, more than that, to design a manipulator which incorporates this device. So to conclude my talk, we propose a toroidal CVT as a variable impedance actuator. This offers a good range of ratio and torque capability. Ratio, as you saw, is changed automatically by the variation of the resistive torque. Thus, the impedance of the device is controlled by the force applied to the toroidal disk. We think this is a good candidate for a passive or active variable impedance actuator. When I say passive, is for example, if the force behind the toroidal disk is just a spring, a coil spring, or other type of spring. But if we control it with a hydraulic or pneumatic or electromechanical way, then obviously it becomes an active variable impedance actuator. So to end my talk, I'd like to acknowledge the financial contribution of the Engineering and Physical Sciences Research Council of England, which sponsored this work. I also want to say that this is a collaboration between my research group and Asama Laboratory of the Department of Precision Engineering, University of Tokyo. And also, I'd like to acknowledge the help and support of my co-investigator in this drug on the UK side, Drs. Godaba, Herzig, and Lee, in alphabetical order, so I don't upset anyone. And also the postdoctoral researcher, Rizwana Parween, and PhD student, Kitmi, Nikala Vitanej. I'd like to thank you all for listening. I'm very grateful for such a great audience. I really thought there would be 1 or 2 people only in the room. But I'm very grateful for that. I'm very grateful for listening. I'm very grateful to Angela and all the colleagues in the University of Tokyo for the organizing, especially Angela, and pleased to meet you in person, Angela. We met many times online, but the first time we meet in person. And also from my side, Dr. Nicholas Herzig for helping a lot with the organization. And that's all from me. Thank you very much.
Thank you, Romeo, for the interesting talk. And we have some time to take a few questions from the audience. And
I know, from your point of view, I only talk nonsense here. So, yeah. Yes.
Models or physical builds, have you done
Yes. Look, this actually was built many years ago as a mechanical prototype for a car, and it did work. We had made quite a few of them. It's 50 kilowatts power, which is quite significant for that time. Unfortunately, at that time we didn't have any special traction to it. We just used normal transmission. Yeah, the efficiency is as good as any other total CVT, going between anything between 89 and 96.
Okay.
Is I had this device actually built also by a French startup company a few years ago, and we did a lot of simulation and calculation and testing, and yeah, it can go to for large power probably over 95. Okay.
Thank you.
Given like you're not manufacturing spur gears, it's friction driven. Is there other like limitations on how much you can miniaturize it?
No, there are not. The only limitation in terms of miniaturization is the contact pressure between the wall. I don't know if you are familiar with Hertzian pressure, probably not. The Hertzian pressure between the disc, and the smaller the element, the smaller the radial curvature of the element, the larger the contact pressure. The rolling element steels, the chrome steel, the 5200 can withstand easily contact pressure up to 3 gigapascal, even 4.5 gigapascal is not for a long time. We designed our for contact pressure of no more than 2 gigapascal, which means it can last forever. In terms of fatigue, yes.
And given that changing the torque changes the axial force, as I understood it, is it possible to put various of these devices in series to have a more wide range of?
We did have designs. We did have design with actually 2 rows, if you want, of balls, if you like. We call it double CVT. Yes, it can be possible to do like that. Yeah, a double row, which obviously will transmit twice the torque in still reasonably compact sum. Yes. Thank you very much.
Okay, so thanks again, Romeo. And now our next speaker is Dr. Robert Skilton. He is the head of research at RACE, that is the Remote Application in Challenging Environment. And I think he will talk a bit about nuclear fusion. So please, the floor is yours.
Thank you. Okay, I'd just like to echo the thanks of the previous speaker as well. It's really great to see so many people here in person for this topic. I think it's fantastic, and thanks very much to Angela for organising this. I'm Rob Skilton. I work at RACE, which is the UK Atomic Energy Authority's robotics lab, where we focus on robotics for nuclear environments, or extreme environments and other interesting environments. Okay, so I've just come here from the FDR workshop, which is looking at robotics research and other research related to decommissioning of Fukushima Daiichi. I know quite a lot of the people in this room have also done the same, and many of you are working on nuclear fission and fission decommissioning problems, which is a very important topic. It's not the only nuclear robotics topic, though. And I'm going to try to persuade you that actually there are some really interesting challenges to solve in the world of nuclear fusion research. So commercial fusion power is closer than ever. We are working on nuclear fusion energy because we see it as the next generation of energy that will meet the zero carbon energy needs of the future. Fusion is cleaner and safer than fission energy and has less challenge in terms of long-lived waste byproducts. We're essentially recreating the process that powers the sun on Earth. And some people say we're making stars on Earth and trapping it in a magnetic bottle. That's quite cheesy, but it is kind of true. And that is very challenging. And it's been a long journey. We've been working on this since the 1950s. It's really difficult. Actually, making fusion energy on Earth and generating electricity from it is very challenging for a wide range of reasons. It's a very complex physics problem. It's a very complex engineering problem where you need complex plant that operates in very extreme environments. And the maintenance of those plants are really challenging as well. That's the reason we haven't got to fusion energy yet so far today. We don't have a fusion power plant anywhere in the world, but I'm hopeful that we soon will. So historically, we've got some devices here. So the Joint European Torus, JET, this is in the UK, and it's currently the world's most powerful, actively operational fusion power plant. This is where my organization has come from. So our background is robotics for maintenance and enhancements of the nuclear fusion experiments in Culham in the UK. We also have a picture here of ITER, the next generation. This is being built in the south of France right now. It's one of the biggest and most expensive science projects that has ever been built by humanity. It's an enormous project and it's highly complex, representing something like more than 50% of the Earth's population. It's an astonishing project, and it's going to have lots of challenges that need to be solved to demonstrate net gain of fusion energy. But we're also thinking about the future and what the next generation of fusion reactors and power plants are going to look like. I've got two examples here. The first is STEP. This is a UK project. It's a spherical tokamak, which aims to generate electricity onto the UK grid. And this is planning to be built by 2040. It's a really ambitious project, and there's often talk of fusion being 30 years away. Well, this is trying to bring it back significantly and trying to really take a high risk and high reward approach to getting to fusion energy faster. I've also got an illustration here of the demo fusion power plant. So this is the EU fusion power plant, of which my organization is leading the robotics and remote maintenance aspects. This likewise is an EU project aiming to demonstrate the commercial viability of fusion as an energy source. So demonstrate that it can be done so that private companies can invest and build fusion power plants and develop the technology required for full operation. So why do we need robotics? We don't have a lot of robotics in operational fission plant. What is the need? So with fusion reactions, we have a very high level of high energy neutrons, which are produced as part of the reaction. This is one of the reasons we're able to generate so much energy from it, but it also results in activation of the components, activation of the steels and the other vessel components, causing a high gamma environment even after the reaction is shut down. The neutrons cause damage to the vessel components, meaning that they need to be replaced. We can't just leave them in there forever. So we need to routinely replace these components. Conventional electronics and systems can't be used. Some electronics and systems can be used, and I'll talk a bit about that. There's a wide range of complex systems in a hazardous environment. These are not simple plants. They need magnets, heating systems, cryogenic cooling systems, diagnostic systems. If you look at a fusion reactor, you'll see it's packed with complex systems which need to be maintained. And so teleoperation is essential. We also have challenges that come from the plant architecture. So the magnets form a cage around the reaction. And what that means is we only have very narrow access ports from which to enter and install and remove components. That means we end up with very slender, long-reach robotics. This is something which is very common to some of the nuclear decommissioning challenges we're looking at in Fukushima, but also in the UK. Components often need active cooling, so the vessel components need to be cooled, which means every component has cooling pipes and fueling pipes attached to it. Pipe maintenance in a very fast, cost-effective way from often only one side is therefore critical. Okay, and the commercial viability. So we need to not just do fusion. We're doing fusion today. The question is, can we generate electricity in a cost-effective way so energy companies can make money from the investment of building fusion power plants? And that means the plants need to be generating electricity, not being maintained all of the time. So the maintenance needs to be fast and efficient and reliable. The drive for productivity pushes the need to rapidly inspect and repair in the most extreme environments. So when we shut something down, we don't want to wait 6 months to have to go in and do an inspection. We want to get in immediately in the vacuum, in the magnetic fields, in the high radiation environment, in the high temperature environment. So we have some very extreme conditions. And then the regulation and commercial drives mean that everything needs to be safe and reliable to levels potentially beyond what we have today. Okay, so hopefully everyone can see an image of a fusion reactor. And this is what we're talking about. It's a giant donut-shaped magnetic cage. This is where the fusion happens. And we can see this is an image from JET showing the plasma, which is heating up and starting to generate the fusion process. We see neutrons, which are radiating and causing damage to the components as well as activating them. So we need to send robots in to do all of the maintenance that needs to take place. This is a video of a sped up video of some of the robotic systems which we've developed and use at JET for maintaining the fusion experiments there. This is something which has taken place over the last 20 years or so. We've had extensive experience of design, build, and operating these types of systems within the hazardous environment that we have in JET. And a lot of these lessons learned and experience is being taken on and being deployed now to other projects and other areas. One of the organizations that was involved in supplying the long-reach arm for the Fukushima decommissioning small-scale fuel debris retrieval and sampling took a lot of experience from these operations that have taken place at JET. So robotics make fusion possible. I'll steal a quote from our director who said, no robots, no fusion. Actually, I think that's true. And if we don't have the robotic technologies we need to get to this, then fusion won't happen. And we won't have this as an energy source for the future. I've got another video here. This is just an illustration of how it's not just about the hardware, but about the digital technologies and tools which are used. This is a VR system which we've developed that is used to maintain the JET reactor, as well as other things. It's a general purpose tool which we're using in lots of areas. But digital tools like this are used to train operators, to develop tasks without access to the equipment or the facilities, to rehearse tasks, do digital mock-ups, which are potentially cost-saving compared with physical mock-ups. And then the digital tools are used during the live operations to support operations, to provide new viewing angles and better conditions so that we can see what's going on in the remote environment. You can see the two long boom robots, which are famous from this kind of operation, one of which deploys tools and equipment. The other carries a dexterous, remotely operated haptic manipulator, which can do the delicate handling tasks. So remote maintenance presents major challenges, and we're here today. I'm here today because I want to tell you about the challenges, because I want you to help me work on them. So we've identified, we've tried to distill some of the main challenges down into the top 10 challenges for robotics and fusion. So there are lots of these. Some of them will be relevant to some of you, others less so. These include things like pipe maintenance, environmental compatibility, waste management, rapid intervention handling, assurance, trust, and regulation. I can share more information on these later. Actually, for today, I'm just going to highlight 4 of these, which I've picked out because I thought they might resonate better with this audience. So I'm going to talk about the slender mechanisms, the long reach mechanisms, the environmental compatibility, the handling challenges, and waste management. And I'm just going to touch on these briefly. Come and talk to me later if you want to get more detail. So in terms of slender mechanisms, confined spaces, typically we're dealing with this type of long reach manipulator. This is a test arm we have available in our facility. It's 10 meters long. And we have lots of long reach robots like this that are relatively flexible. They deform in their joints and in their lengths. And we have issues with deformation and vibration control. Similarly, a test concept which is being developed as part of our UK-Japan collaboration in order to investigate some of the issues of long reach operation into decommissioning plant. So what can we do here? Modeling and control methodologies can potentially allow us to predict and measure the deformations. We're also very interested in control techniques. So this shows some work that's been done on controlling out the vibration. So applying control techniques that reduce, eliminate the vibration and allow us to control that. And we're also very interested in digital technologies and digital twin tools that can predict and simulate those vibrations and deformations. The radioactive environment. So I mentioned the very high gamma. Actually, when we compare future fusion reactions to future decommissioning scenarios, fusion has very high gamma radiation, and it's something that we really can't ignore. So we're working on highly radiation tolerant devices. This includes things like semiconductor electronics, optics, and polymers. And actually, there are already some technologies that are very good in terms of high radiation electronics. So I would advise everyone to look at a company called Magix in the EU, who are developing radiation hard semiconductor devices, which we are using, and probably very applicable to a lot of what you're doing. But actually, it's not just about the electronic devices. This slide talks about diamond electronics, which is something we're using as opposed to silicon. But I'm also going to mention the fact that there is a lot of work to do in planning. So planning, mission planning for autonomy and avoiding the radioactive conditions and dealing with the degradation in system performance. I know a few of the UK universities are working heavily on this. Third challenge I'm going to highlight is handling. And I don't know if this video is actually going to work. The link. So the previous 2 talks have talked a little bit about handling. I know Rich Walker is doing some great work in Shadow on dexterous telerobotics. We have some similar challenges. That might work. So there is a lot of work developing remotely operated handling technologies that can not only do the delicate handling tasks that are required, which is really important. We can play Jenga, but actually, can we play Jenga in a nuclear environment? Can we play Jenga with high radioactivity and contamination issues? And it turns out the answer is yes, but it's very, very difficult, and we need a very different level of performance. training operators to use these types of devices is challenging. And some of the work that we're doing in UK is looking at handling inside very confined spaces of glove boxes. So this is something which is really important for decommissioning in the nuclear industry. But it actually represents a common challenge of handling delicately in confined spaces like we see in fusion. And this means we can maintain systems, maintain robotic systems in hot cell facilities without people having to go there. I don't know if Barry's going to be talking about this, but he has some excellent work in this space. In order to train operators to use these systems, we have huge challenges in terms of getting access to the system and having the availability of systems for training. So we're doing work on developing haptic training simulators, and we've welcomed more work in this area. So the question here is, how can we train operators to use these systems in a reduced amount of time with reduced access to the equipment that's needed? And we think digital and simulation tools are one route to achieving that. And then the last challenge I'm going to talk about is waste management. We have a lot of contaminated, activated, hazardous waste that needs to be managed. And there are lots of challenges with handling, inspecting, and maintaining those facilities. I've got an example here of some work we did with the University of Oxford, who are very close geographic partners, on automated inspection inside nuclear waste drum stores. And you can also see some images here of similar technologies which have been deployed to inspect the interior of fusion power plants, fusion devices, which is really critical for maintaining the condition of the plant. So why you should be working on fusion? Actually, fusion is a really important energy source for future generations. It's extremely challenging, and we need lots of people working on the robotics aspects of solving these problems. We need new advanced robotics and associated technologies across all of the areas which are relevant to this workshop. There is a huge increase in research funding and private investment in fusion. So if for no other reason, fusion as a use case might help you secure that research grant. And we'll be solving other challenges along the way. My organization is focused on fusion, but actually a lot of what we're doing is relevant to decommissioning, and thus we're working heavily in the decommissioning sector. So get in touch with us if you want to, build collaborations, and please take on fusion as one of your use cases in research. We've produced this guide which summarizes the top 10 challenges in fusion. I've got some physical copies with me if you want it. This QR code should give you access to a digital version of it. And the idea behind this is to communicate the challenges so that you can use these as use cases in your research, and so that you can identify ways for your research to have further benefit in the fusion world. That's all I'm talking about today. So thanks very much, and happy to take any questions.
Thank you very much, Rob, for the talk. Please, if you have a question, you can go to the microphone.
Yes, thank you, Robert, for your presentation. Just a challenge one, you talked about vibration. What is the source of the vibration?
That's okay. I'll repeat the question. So challenge one was about vibrations and where is the source of the vibrations. The flexible deformation in these long reach arms. So we have very long arms with very high payloads on the end. They're essentially a long flexible pendulum with joints in between. The joints typically have high ratio gear transmissions. So things like harmonic drive gearboxes in the joints, which are a source of elasticity. And depending on the control scheme, you often see lots of vibration and flexible deformation. We also have to deal sometimes with components which are flexible. So say a 10-meter long, 100-ton component, which contains some level of fluid. They are flexibly deforming and vibrate when we move them, but actually we have no sensors on them, so we can't even measure what's happening there. So we have those sorts of challenges to deal with.
Thank you.
I'm curious now to know who's going to win Jenga. Is it going to be you or the Rich Walker?
The Rich Walker's system is really good and probably will win. But if we put it in the fusion reactor, I'm not sure it would be the same.
Well, a more serious question. Inside the reactor, presumably the dose is from activation of impurities in steel. So do you know how high is it in grays when you send mascot? I mean, is it tens of grays, kilograys, megagrays?
Yeah, so in jet, the activation level is very low. It's much lower than even decommissioning type tasks. The simulations of activation in future fusion power plants show something around the 1 kilogram per hour rate. So it's extremely high, and for conventional electronics, we're talking about less than an hour's use, something like that.
Are you doing anything with augmented reality headsets for user training and situational awareness?
Yes, so we are doing work in augmented reality for situational awareness, user training, and things like so we have a spectrum of environments where there's robot access environments and human access environments, but there's a crossover point. So there are parts where humans need to go into a slightly hazardous environment and do tasks that interact with the robot. For example, loading components. And we've been doing some work on using augmented reality for that type of situation. I think there are loads of applications for augmented reality in telerobotics for fusion. So if anyone wants to work on some of those, please be my guest.
Thanks a lot. First of all, super cool problem. I would like to understand the following, taking an example. So some of this, my question is the role of autonomy of robotic systems in this type of, in this application you have in mind. So I guess a lot of the things are maybe unknown a priori, but you mentioned, for example, let me just talk specifically, planning to avoid radiation, right? How much of that is based on a lot of knowledge a priori in the environment? How much of that has to be reactive? How fatal is the error from the robot, right? It goes accidentally in a too radioactive environment. Can you give us some hint about what are the major challenges when it comes to autonomous systems in this environment?
Yeah, so firstly, autonomous systems are necessary for fusion. We can't teleoperate everything because the number of operations and robots that's needed doesn't scale. We need too many for human operation. Fusion power plants are somewhat a known environment. We build them so we know what's in there, but not fully. There is a lot of uncertainty, and in particular where we're predicting where the radiation areas would be, there are errors associated with that. There are assumptions and simplifications. So there are challenges for robots operating in the radiation environment, and planning for operation in the presence of radiation hazards is really important. With fusion robotics, everything needs to be recoverable. So if your system fails, you need to be able to get it out somehow. That adds a layer of complexity on top. And with autonomous systems, we don't want robots to be failing and causing blockages and preventing access to areas. So there's a lot of consideration there. The other area is the trust and regulation area. So convincing nuclear regulators that an autonomous system, maybe using AI, is going to be safe and not cause any challenges, any additional hazards, is a big challenge. That's something we're starting to work on, and I think that a lot of work on that needs to be done around the world. Thank you.
Thank you very much. And if you have more questions, we will have different tracks, so please go and talk. And for the next contribution, for the next talks, we will have the 4 contributions. So every speaker will have 5 minutes for 2 minutes question and answer.
Yeah. You get it.
Okay, and the first contribution is about the radiation source localization via mobile robot by integration of filter back projection, and will be presented by Fujino.
Good morning or evening. I'm Fujino from the University of Tokyo. Today, I will talk about the radiation source localization via a mobile robot by integration of filtered back projection. First, I'd like to give you some background about the radiation source estimation. High radiation environment has a risk of radiation exposure for humans. The accident at the Fukushima in 2011 caused much radioactive substances to be scattered around the wild area. Also, there have been reported many nuclear incidents. In such situations, we need to shield the substances with least to make the environment safe. So the estimation of radiation source distribution using mobile robots is necessary because robots can enter such a dangerous environment. In the radiation estimation, a sensor called Compton camera is usually used. This sensor detects gamma rays emitted from radioactive substances. When a gamma ray gets into the sensor, the scattering angle beta is calculated, and therefore the location of radioactive source which emitted the gamma ray is restricted on the cone surface called Compton cone. Next, I will show you the related work of radiation source estimation. Generally, voxel-based methods, which means dividing the image space or world into voxels, are used. Simple back projection is a method to get distribution from radiation measurements. This method projects all Compton cones to image space, like the light figure. So the more Compton cones are projected, the more likely to be the source location. The maximum likelihood estimation maximization is a statistic method. This was developed to get more accurate solutions of radiation distribution, but has a constant that calculation is time-consuming due to the voxelization of the world and necessity of many iterations. So the objective of this work is to propose a method to quickly estimate locations of point-like radiation sources. Before explaining the method, I'd like to clarify the problem settings of this work. The problem to solve here is to estimate the locations of point-like sources cesium-137. The number of radiation sources in the world is known. The environment is indoor, and there is a robot that has a Compton camera to detect gamma rays and a LiDAR for SLAM. Here, I briefly introduce the general algorithm of radiation imaging used in this work. The first step is a spherical single back projection, and this method projects all Compton cones to a sphere like the light figure, and we don't need to divide the whole space into voxels. The second step is a filtered back projections developed to reduce the blur of simple back projection. Using this can make the image sharper. Now I explain the proposed method. The proposed method consists of 3 phases. First, a robot moves and stops at several points. Then at each point, we get peak points from each filtered back projection results by finding local maximums. And finally, the source locations can be estimated as the closest points from the corresponding 2 lines. This method can quickly estimate the source location without voxelization of the image space. Here is the result of the simulated experiment of radiation source localization. The objective of this experiment is to validate that the radiation source locations can be estimated by the proposed method. The experimental settings were written here. And I explained the results. 2 radiation sources were put in the house, and the robot stopped at 2 points, shown in the light figure. The table below shows the estimation errors of radiation source locations, and they are both under 0.5 meters. Finally, I'd like to conclude my presentation. Estimation of radiation source distribution via mobile robots is necessary for human safety in high-dose environment. For quicker search for radiation sources, we propose the method to integrate the filtered back projection results. The proposed method successfully estimated the source locations, and the positional errors are under 500 millimeters. The future work is to consider the structure information of the environment to get more accurate solutions. Thank you for listening.
presentation, and we have time for a few questions. So if you have any questions.
If I understand correctly, what you did is you trying to identify the source location within the image frame, right? So the source location, relation source location can be identified within your camera image frame.
Yeah.
How can you correlate that to a spatial, 3D spatial location of the source when you put your system on the robot? Do you need to do any other further steps to find the actual related source, for example, within this room in a 3D structure? Or we just propagate to where the source comes from?
So you mean, are there any steps to?
Yeah, because if I understand correctly, what you talked about earlier is you can't identify the radiation source within your camera frame.
Oh,
But not necessarily to where the source comes from in a 3D space. How did you manage to find the actual source location when you do the simulation? When you put your sensor on the robot, how can you find the actual source location?
in 3D space?
They're performing SLAM on the robot using a LiDAR.
Yeah, but you'll know the map and where the robot is. Not necessarily, I feel that might be a further step to find out where the actual source is located in the 3D environment.
I mean, if you have the transform from the source to the camera and transform from the camera to the robot and robot to the world, then
Yeah.
you have your
Just
transform
probably where
trained.
it is, yeah. Then you have a further problem how many search for it.
In the last slide,
Yes, I integrate the 2D image results.
Yeah.
So this method can estimate the 3D location.
yeah, the next slide.
Please move on to the next slide.
The last one.
I understand correctly, your camera gives you a bearing measurement where the source comes from.
I think that SLAM is up there shows correct. 3D scan.
I think, yeah. In the middle figure, the green and red boxes are the estimated position of radiation sources. So this method can estimate in 3D space. Thank you.
At the beginning, you said that this problem was for an unknown number of
yeah.
radiation sources, but I don't understand why that constraint is necessary with this method. Like, do you need to know that you have 3 sources, or with the images you could find that?
Yeah, for simplicity, this work make an assumption that the number of radiation. So the problem is to find local when we find local maximums in the filter 2D images. So when the number is unknown, we need to make another algorithm to find unknown local maximas, and this is a little bit difficult. So this time, make assumption that the number is not known. Okay, thank you.
Okay, thank you very much. If there is time during the coffee break, if you want to discuss, please take the opportunity to talk about your work. And now we have the next contribution. Okay, that is. Okay, and we will have a paper that is about systematic database search method for goal selection in redundant manipulator path planning task within nuclear glove box, and is presented by Kat Stylewood. Please, the floor is yours.
Hi, everyone. Yes, I'm Kat, and with my supervisors, Tom Scott and Antonia Semenaki, we've been working on redundancy handling for a redundant manipulator working inside of a confined space.
Okay, sorry, can you turn on the camera so the camera on the screen? So,
Excuse me, sorry. Oh, okay. Yeah. Sorry about that. So in post-operational cleanup, during nuclear decommissioning, operators have to put their hands inside of radioactive environments to perform dexterous tasks in a highly confined space. This has a lot of risks and it's a very difficult job to do, so industry is looking for robotic solutions. Since working in such a confined space, oh no. Excuse me. So since working in such a confined space, a redundant manipulator is a good option because it's able to achieve a continuum of solutions whilst holding the gripper at a single position. So this means that you're able to achieve the goal, even if you are near to the wall, you can simply move the elbow. Is this not working? Oh, sorry, my videos don't seem to be working. It's okay. However, this presents a challenge to a robot controller because a path planner works from a manipulator starting configuration to a manipulator goal configuration. So you need a set of joint angles that you start at and a set of joint angles that is your goal, and the path planner finds a path between the two. However, when we're working with a normal task, we know only the starting configuration and we know where we want the gripper to go, but we don't know what the goal configuration is. So this is, sorry, my videos don't seem to be working. It's a Windows presentation in a Mac, sorry. However, we can, this is done by randomly generating the solution. So working inside of free space, I apologize, my entire presentation is made of videos and they don't seem to be working. Excuse me.
okay, so if you want, if your video are not working, you can log in the Zoom and use your computer, and I move to the next presenter.
Oh, no, it's okay. I can just talk. So the main challenge is that you have to select from a continuum of possible solutions the goal that you can use. And if you're randomly generating this goal, the path planner finds it very difficult to find a path between the two. So ideally, what we would want to do is to intelligently select the goal so that we can have this nice ideal path that we can find between the start and the goal. In order to intelligently select, we have generated a large database of possible manipulator configurations, which we can scan and use numerical operations on to try to find the most ideal manipulator configuration as a goal for a given planning task. So we've used a database management system called SQL, in which we store a large number of manipulator configurations where we hold the end effector Cartesian position, the end effector orientation, the manipulator configuration, which is a set of joint angles, and we also hold the manipulator joint's Cartesian position in space as well. So we know where the robot is in space. So we can query this by using a simple query like select a manipulator configuration where the end effector is at the end effector pose, and then we can do some numerical operation to filter it. So in this very simple one, we've ordered it by joint 1, so it's found a manipulator configuration which has the minimum value of joint 1. If you have an environment with a wall in, you can then also do some numerical operations on your returned results so that you can find you can find a configuration where the elbow is not in collision with the wall. So here we've just simply found a manipulator configuration which matches the end effector requested pose, where all of the joint Cartesian positions are on the negative X side of the wall. So when we're actually planning with this inside of a glove box, we have our planning task data, which is our starting configuration, where we want the gripper pose to be, and any information on the environment. So in this case, where the manipulator walls are. And then we can then use this to select an optimal manipulator configuration for this given planning task. We've tested this using 50 path planning scenarios, starting with 5 randomly generated configurations inside the glove box and trying to find a path from there to 10 randomly generated manipulator gripper orientations, sorry. And we tested this using our database lookup method, where we send all of the planning data to SQL and we return what we consider to be the optimal goal configuration for that given planning task. And in this case, we've defined optimal as nearest in joint space to the starting configuration. So each of the joints are as close as possible to where they're starting from, so you have a much shorter path. It's a little rudimentary, but it's a starting point for us to test if we've sufficiently sampled our database. We compare this against simply randomly generating solutions. So we introduce a random element to help us solve the inverse kinematics. And we find a random solution at this given gripper goalpost, and we try to plan a path to that from where we're starting. Oh, some of these are working. Okay, so you can see in yellow the paths that were generated. So on top is the randomly searching method, and you can see the goal is in kind of the ghost shape. And you can see it's very different each time it's done. We attempted each of these scenarios 100 times, so we're just showing 4 of each method here. But you can also see that the success rate of this one was very low. So it's a success rate of 20% when you're randomly generating a solution, because you're not generating a solution that's optimal to your planning task. We compare this to our database lookup method because it's systematic. Every single time you run the same planning task, you receive the same goal configuration, and it generates a very similar path each time. So across all of the 50 tasks that we attempted, you can see the bottom left is the success rate, which is for our database lookup method, which is in dark purple there. It's either 100 or 0. So every time you try to do the same task, it will either succeed every time or it will fail, with the exception of scenario 17. In comparison, you can see the orange is the randomized search method for the goal, and this has a higher success rate of 20% only, so it's very low. So if you're an operator and you're trying to send your gripper to a certain location, you can't be sure, you can't have any faith that it's not getting there because it hasn't found the path, or if it's not getting there because the path is impossible. So you can't really trust your system like that. You can also see the path length that was generated in the top left. So in dark purple, they look like very small dots. This is 100 attempts, and every time it finds a very similar path. We compare it to the in orange, which is when you've used a randomly generated goal configuration. There's a very wide spread, which means every time it does succeed, it's generating a very different path each time. So it's not very repeatable. And then the most important one is the time taken, which is the big graph on the right. In purple is the database method. So this is the time it takes to search through a massive database of over 1 billion configurations to try to find the ideal one for this task. And you can see it does take longer during the attempts than when we use the random search method, which is the orange along the bottom there. However, this is only for the successful attempts. It doesn't take into account the number of failures you have to go through when you're iterating many times in order to reach the solution. And that's shown in green. So in the little green triangles is the amount of time it takes before the very first successful attempt was run. So sometimes it gets lucky and it's a bit quicker when the triangles are a bit low, but for the most time it takes much longer. So thank you very much for listening. I apologize for my lack of videos. Happy to take questions.
Hi. So the database, are the solutions evenly spread, or is there a more intelligent sampling mechanism there? And also, how long does it take to make the database?
Yeah, so how long it takes to make the database just depends on how much computer power you have. I used Amazon Web Services, AWS, and it took me quite a long time. But yeah, it takes about 14 hours per Cartesian point. So here we've got the sampling. So you can see the purple dots is the robot's workspace that we've sampled. And it's done every 5 centimeters in Cartesian space. And then the bottom, which is the big sphere of like directions, that's all of the orientations we've done. It's about 7,000 at each one, but it's equivalent to sampling every 10 degrees. So then at every single one of those gripper poses, so all of the orientations at each point, we sampled the manipulator configurations across the entire sweep of the elbow. So the video at the start, which was missing, basically showed the robot gripper staying still and the elbow doing this. So we sampled 10 degrees of the elbow motion. And then for each one of those, we looked for this symmetry property, which I think the video was working for that one. So maybe I can show that one. but it's this one. This one on the left. So you have a very similar physical position in space, but if you swap the joints around by 180 degrees and you have a manipulator of -1 on some of them, you can get this like symmetrical property. So we searched for that as well to kind of make it enveloping all the possible configurations so you could select the ideal one.
There is also a question from the Zoom. Can you show better? Yes, you cannot read. What's the general runtime lookup configuration?
So just jump back to the end. Excuse me. So on the right, we can see the time taken to look up the configuration. So in purple is, well, this is the time to look up and also find a path. So there's a little bit of variability there, but it does take a couple of seconds to look up and find it. So it is slower than if you randomly generate a solution, which you can find a path to, because that's very quick to randomly find a solution. But if that solution that you find is not, it can't get there from where it's starting from, which it finds very difficult to do when it's in such a confined space. Yeah, that will then take many iterations. And because of the low success rate, it takes longer. I hope that's sufficient.
Okay, I think that's all. And we have the coffee break. Please take the opportunity to ask more questions and talk. And also for the speaker, if they log in the Zoom, they can answer one question that we cannot here because of time. And now,
okay,
thank you.
Thank you very much.
Okay, yes. So now the next speaker that will join online and is Alex Navarro, and we'll talk about complete coverage planning in nuclear environment using off-proximity sensor with 3D obstacle geometry. So
first off, can you all hear me okay?
Yes.
All right, awesome. All right. Hi, everyone. My name is Alex Navarro. I'm a grad student at University of Texas at Austin, and I'm going to be talking to you about a project we've been working on, which encompasses complete coverage planning in nuclear environments using an off-center proximity sensor, taking into account 3D obstacle geometry. So first, a little background into the motivating application. Polonium-210 is a radioisotope of plutonium, which primarily emits alpha radiation. And therefore, any facility working with plutonium needs to closely monitor for any type of alpha contamination. Alpha emitters are generally harmless when exposed from outside of the body, but if they are ingested or inhaled, they can be quite damaging or even fatal. Unfortunately, alpha is very difficult to detect because it only travels a few centimeters through air. And therefore, in order to accurately measure alpha radiation, you need to be very close to it, either by swiping a surface in order to get a sample of whatever you're trying to measure, or placing a detector very close to a sample surface. And so what our lab is proposing as a general solution for a floor survey of alpha radiation is to mount an alpha radiation scintillator to a mobile robot so that it can provide routine alpha survey. This increases worker safety and the repeatability of results, and also reduces costs in the form of man hours of people required to actually perform these. However, as we started to, implement this in our lab, we discovered that having the sensor out front like that does provide some interesting challenges. So just a quick recap of coverage planning before I get into the exact solution that I'm going into. For any who aren't familiar, coverage planning is the field involving generating a path which applies a tool or a sensor to all the available locations in a workspace. You can think of a Roomba trying to clean the floor. One method to do this is through grid decomposition. I have an image of that here. But there are a number of alternative methods, which I'm not going to go into for the sake of time. But one thing that we noticed with pretty much all of the existing literature about coverage planning is that there is this assumption that the robot and the sensor are coincident or concentric, which doesn't apply to our case where we have the sensor out in front of the robot. And changing the navigation frame from the robot to the sensor provides a number of challenges, but interestingly enough, also provides some additional opportunities to increase the quality of the generated path. But first, let's just take a look at how we are going to solve this. So we noticed that we want the sensor to be the main navigation frame so that we can make sure that the sensor reaches everywhere in the environment. And so what we do is we break up the robot into composite bodies. You have the sensor as its own body, and then the robot as one or more other composite bodies. The number is up to the user, but the main point is that the sensor and the robot are considered differently. Now, each one of these objects has their own obstacle interpretation of the environment. So what one of them considers to be an obstacle is not necessarily going to be true for another. And this is kind of what gives us that increase in quality, is now we can have the sensor, which has a different obstacle interpretation of the robot, go into areas which the robot itself cannot fit in. You know, it kind of resembles an insertion task for a manipulator, which generally speaking has a much more robust collision detection model than a mobile robot. And it also gives us a secondary optimization that we can mark unexplored areas as obstacles for the body and not for the sensor. And that will prevent the wheels from tracking contamination through a facility. And the main challenge that we face is that orientation of the robot now carries much more weight than it would in a traditional coverage planning problem. You can see that here in this example where the sensor is in the same location for these two example robot poses with the sensor under a table. But the robot's in a very different state regarding the actions that it can take from this position. And so a full 2D pose of the robot is required at each step in the coverage planning algorithm in order to maintain tractability. Now, to achieve this, we segment each grid cell into its set of allowable orientations for where the robot can be. Each partition, we call these partitions. Each partition encodes a valid robot pose, which places the sensor at the center of that grid cell. Now, these partitions can be connected to partitions of neighboring cells to form a fully connected graph. Now, since these partitions are all connected to each other and they represent valid poses for the robot, we can now substitute these partitions for the original grid cells that you would use for traditional coverage planning algorithms. And we can actually use the exact same algorithms in almost the exact same way to generate our coverage plan. We have tested this method in simulation in Gazebo. On the left is the simulation environment that we used. And you can see in the top right, the obstacle representation for the robot body in gray and for the sensor in black. You can see how the available space for the sensor is significantly more relaxed than what the available space for the robot is. And in bottom right, we have a simulated coverage plan, admittedly without the distractions of not knowing where everything is in a real world. But you can see that if the plan is executed perfectly, the coverage that it generates is very complete and fairly efficient. That's the end of my presentation. I'll take any questions.
Thank you very much for your presentation. And is there any question from the audience? Please raise your hand and go to the microphone. So, great.
So thank you for your talk. Can you hear me or?
Yes, I can hear you.
Okay, so perfect. Did you somehow account for like an optimal solution? Because right now you said, okay, we have like these coverage where you say, okay, these angles, and then you just have like an algorithm connecting all this. So which coverage to which coverage can be connected. This isn't like a single solution, could be multiple solutions. have you like tagged this problem as an optimal problem, or just find any way where it's the solution?
So what I'm contributing here isn't necessarily the coverage planning algorithm, which exists in literature. They have their own ways of achieving optimality. What I'm doing is I'm finding a way to convert this problem with an offset sensor and a non-holonomic base, which includes a lot of restriction, and kind of generalizing it into a form where I can apply those already existing solutions. So the question of optimality, I would say in this case, doesn't fall to me.
Okay, thank you.
Is there any other question? Is there any question also from the online audience? Okay, then thank you very much. Thank you for joining. And maybe if you have a question, you can log in online and ask question anytime. And now we have the next presenter that should be here. Okay, it's not here. Ah, yes, please. Fine.
I don't have internet access to.
Okay, so I can try. No, it's not needed actually. Yes, so you can use my computer. Is that okay? Okay, for the next presenter, also for the afternoon, if you want to use our laptop, please come during the break and give the presentation during the break so we don't lose time. If Alex is still online, there is a question. Maybe you can answer on the meantime I prepare the next presentation. Alex, are you still there?
Yes.
Okay, you can read on the chat. You have a question. Okay. Okay, Alex, you can answer on the question, can? On the chat. Ah, okay, you answer by chat. Okay, thank you, Alex. Okay, the next presenter will be Andre, and we talk about optimal sensor launching with UAVs for monitoring of hazardous environment.
Cool. So, hi everyone. My name is Andre. I'm with the Imperial College London. I'm a PhD student, hopefully finishing soon. And I'm presenting today a project I've been working on which relates to sensor placement for hazardous environments using UAVs. So this is a bit of a generic problem. So you know that UAVs, you can fly around a lot for like long distances. You can cover wide spaces, and you can map out whatever quantity you're trying to measure with like a good temporal scale, a good spatial scale, but not so good temporal scale if you want, because just flights are not available all the time. So one way to work around that is to do this mapping, fly in this environment, but also place sensors that will allow you to continue this measurement on a localized area on a better temporal scale. Now, for industrial environments, the way to do this, because you need to precisely place the sensors, is to actually go close to the surfaces, place the sensors, and fly off. But this can be risky if you're like in constrained environments. And this is what I've been trying to approach. So what I've been working on is on launching the sensors towards whatever you're trying to measure. And there's different ways to make them stick. And then you fly off and you never need to get close to any obstacles. So the way this works is you have like a regular multi-rotor with sensors for positioning, nothing out of the ordinary. And then you have here like a little, what is basically a spring-loaded cannon mounted on a servo, which allows you to launch the sensors. So this is previously published work. It's like this miniature SMA-driven mechanism. You attach a sensor to it, you fly off, you detect a target, you launch the sensor, and it hopefully stays there. And there's multiple options in terms of what can actually launch here, because you're obviously limited in terms of payload, but nowadays, even with just consumer grade electronics, you can do stuff. For example, the top one that measures temperature, humidity, and forwards the data via Bluetooth could measure, for example, leaks on like cooling loops of whatever facility you're experimenting with. You can do condition monitoring by having an accelerometer and just forwarding like relevant information. So I've been doing real-time FFT and just thresholding peaks. So it's quite simple, maybe not the most advanced way to do this. And you can also have like solid state radiation sensors, which are maybe not the best performance, but at least fit into this method. So in terms of applying this to nuclear environments, I'm hoping to do this in a jet, which Robert has so kindly described for us previously, and what are the challenges in there. Yeah, and they've always paid for part of my PhD, which is great. So thank you. And so in terms of what I'll be targeting in the facility is not quite the actual reactor. There's just too many expensive things in there that you wouldn't want a drone to crash into. But there's lots of external components that need to be monitored and maintained as well. So Robert mentioned pipes, right? So all of these equipments that manages cooling and heating of certain elements, they're not quite reachable by ground robots, for example. And their UAVs can have like it's an easy application. So you have like a fast response times. You can reach areas at height. And I'm aiming to target these leak detections in these cooling loops, but also structural health monitoring of the supporting structures that you have around the reactor. So recently I've been looking a bit more in depth into how to model these trajectories of the sensors in flight and how to do this quite cheaply in terms of computational power. So the main challenge in terms of modeling this is that a lot of the aerodynamic forces are linked to like this pitch and yaw oscillations of the projectile. And that would normally, as an aerodynamicist, the trend is to actually describe the system really well, CFD, wind tunnels, whatever. But if you're aiming into having multiple sensor packages and want this to actually be useful, you can't be doing that for every sensor. So I've been looking into ways of using classical aerodynamics to simplify the system. And what I've been trying to do is to achieve similarity in terms of pitch oscillations. So basically sizing a tail stabilizer that allows me to have similar flight behavior for whatever sensor you're launching. So it would make the trajectory independent of the sensor mass and of the shape of the sensor. Sort of, you can see here, experimental results kind of match with what we expect with the model. Furthermore, after you do that and you have similarity in pitch, you can get rid of pitch. You end up with a mass like a particle subject to drag being flying around. And the advantage in that is that the problem is not dependent in time anymore. It's only dependent in space. You can solve it a boundary value problem. So you can set final conditions on impact. For example, you can have an idea of what the morphology of the surface is. So you force it to impact perpendicular to the surface. But also if you know what sort of contact you want. So if you have a magnet, doesn't matter too much as long as the force is not too great, you won't bounce back. If you're using adhesives, for example, you need to really tightly control like how much impact force you have, otherwise it's never going to stick. And this suddenly becomes almost like a contact interaction problem, because you can control your final conditions through an optimal problem. Yeah, and besides solving it as a particle mass subject to drag, you can also insert like kind of a virtual drag term that is related to where the pitch oscillations normally occur, which is normally when you have the greatest curvature in your trajectory. So it's a bit of a quick and dirty way to actually get a bit better results than what you would be able to otherwise. So with this, you can define an optimal problem. And also I'm using just a very cheap perception. I'm using this rangefinder to detect where the target is, but also it's mounted on a servo. So I also do like a quick scan 90 degrees to see what's in front of me, and use that, feeding that into the optimal problem to keep just the UAV away from anything that could be in the way. Well, the UAV and the sensor when it launches. So you have here a few examples of just scanning of like, these are like just areas with like a bunch of cooling pipes in a nuclear facility. Sorry, not a nuclear facility, it's just an industrial facility. And then the system finds a suitable position and angle to just launch the sensor and make sure you hit it properly. In terms of experiments, we have here, for example, in the forest, where you have a spine embedding this into a tree, or lower below you have it with a magnet launching it towards a metal plate. One of the things that well, people were mainly concerned about was that when you're actually launching this sensor, you of course have like the reaction force that makes your UAV fly backwards, and that has mainly an influence in pitch. However, the cool thing about this is that this wasn't really intended, but it just works in our favor, is that when the sensor is being launched, it's only contacting the spring where the energy is stored, and it basically works as a flexible mechanism, and it's floating, and the pitch of the UAV doesn't have an influence on the sensor as it launches. And I mentioned here like how contact force is important. So here we're using adhesives to try to place this into a wind turbine. And as you can see, it fails if you're not using like the full system and actually try to like place it near the apex where you have less contact force. In terms of accuracy, like this will depend on like what angle you're launching at, but that can be characterized. And I'm comparing here to like using this like just the maths I showed you, and the option of not considering drag at all, which is like just simple, quick and dirty way to do this. In terms of how it compares with like contact placement and direct manipulation, it's pretty comparable depending on the distance you're launching at. So that's a pretty good result. So in summary, yeah, we can achieve this like with pretty much the same accuracy as you could by just directly interacting with your environment. You can do that safely from a distance, but also you can do it using like quite minimal perception and computational power. So like the system I built is like around 1 kilogram, so it fits into like pretty small, tight spaces. And wait. Yeah, and the optimal launching problem allows you to like kind of navigate these systems, these environments, and just make sure you can place your sensor without hitting anything. Yeah, thanks. And
Thanks a lot, and we have time for a few questions. Do you have any questions? So, like you mentioned about the correlation between the angle in which, can you show again the graph
which one?
about the this one, like when you launch, the launching angle?
Yeah.
So can you like
Why is there relation, this
Yeah.
relation? So I mean, the greater the launching angle, the more like kind of like parabolic your trajectory is. And as I mentioned before, it's in when you have greater curvature of the sensor's trajectory is when you have greater influence from the pitch.
Okay, so you do some pre-prediction of this trajectory?
Yeah.
Okay. And it's matching in all the environment you tried, it's matching your prediction. You take in consideration.
The environment.
Yes.
Why would you think they would have an influence? Like the
Yeah, you think it's influencing or not?
I mean, the environment, as far as I would say, has a greater influence is more on like the positioning of the drone because you're using visual methods to do position control. In terms of like the trajectory, unless there's wind.
Yeah, these are also
Okay.
because you also did the experiment
Yeah.
outside, right?
Yeah. So I mean, even outdoors, I'm targeting quite clustered environments. So I'm doing like under canopy of the forest.
Okay.
Where you normally don't have as much wind.
Yeah, I understand you.
So
your application is for inside, but I saw the video in.
Yeah.
So I thought about the wind.
Yeah, it's still like like if you're in open environments, there's other methods that will suit this better. Yeah.
Okay, thank you. And do you have any question from the audience or from the top, please? Check if it's on. Maybe so. Maybe it was on.
Hello. Yeah, I think that's on now. Hi. No, really cool work. You mentioned the issue with the sensor rebounding off the surface and the importance of the contact angle, and you've informed your planner. I was wondering if you'd done any prototyping around the tip of the sensor. It seems like you might be able to create like a passive mechanism that helps align the sensor end with the surface. Is that something you've considered, or it just turned out that it didn't matter that much?
I haven't really characterized it, so I've been using these like 3D printed frames for the housing, but I have added like kind of like flexible beams to the tip.
Yeah.
So it does have some like it does have some flexibility and adapts a bit to the surface. Even because like the optimal problem I'm solving, it's got like multiple objectives, so it's not really like it's not really sure that you'll have like a 90-degree angle when you hit. It'll be around that, hopefully.
Yeah.
So that should allow to improve that a bit. But also, yeah, so it's another point is that it would dampen a bit the force. So far, I haven't seen it make as much of a difference, but it just needs a bit more effort and work put into it, really.
Yeah, great, thank you.
Have you considered using the propulsion of the UAV itself to impart initial velocity when launching?
Yeah, yeah, that's definitely a possibility. Yeah, I haven't looked into that yet, though. Yeah.
Okay, my last question. Okay, so thank you very much. We are a bit late at the time, but okay, let's have anyway the break, 10 minutes break, and after have the last talk of the section. Thank you very much.
Thank you.
I'm sorry we are running late, but let's have 10 minutes break. So I think everybody a bit refreshed, and after we can have our last talk, but we will have 2 hours break for the lunch. So please don't run away. So it's last talk.
to give opportunity for robotic systems to go, perform characterization, and potentially also assist in the commissioning in either previous sites like a Hanford site or existing operational facilities for nuclear power generation. And of course, there is also a host of abandoned uranium mines that exist all around the world. Some of them actually were in Nevada where we were before, and we had the opportunity to get some pretty cool data sets, all within, of course, safety and regulations followed by our radiation advisor. Now, of course, before I go into the aspect of radiation characterization in these environments, the first thing I want to mention and give a pointer to previous work of my group that finished in this particular application in September 2021 is the ability to go through the most extreme environments. The video plays very erratically on the projector, but I'm sure you understand that there is a flying robot there exploring an underground mine with full autonomy. There is no human teleoperation whatsoever. And actually, the only thing that the human had to provide was a bounding box of the area to be explored. This was actually part of the preparation for the DARPA Subterranean Challenge, which finished in September 2021. And myself and together with my partners from other universities, we had the opportunity to win the competition. So actually, for us, all this idea of facilitating robotic systems that can characterize waste facilities was highly linked with our activities in the DARPA Subterranean Challenge, primarily in terms of the localization, mapping, exploration pipelines. But I'm not going to bug you with all that. We have given a lot of presentations for this. What I will talk about more is how we actually go about the aspect of radiation characterization in this environment. So we wanted to build a very thin, a very simple system that will be able to not only map the world in 3D, as many of our other robots could do, but also provide gamma radiation intensity estimations and also spectroscopic analysis in any part of the environment that we'll explore. And again, out of the motivation of my group, the idea is that you know nothing about the environment. I'm not saying that you shouldn't know, but if you don't know, this is where our methods work the best. So let me try to explain this step by step, how this works. So I think the audience is kind of more specialized. I had some slides for people that may not have any background in radiation characterization, but anyway, just for this audience, I'm not going to go into detail. So we use scintillator from psionics. Of course, we exploit the fact that we have inverse square law principle between the intensity and the range, and we have Poisson statistics that we have to obey with respect to the distribution. We were able to characterize the spectroscopic response of different materials, like for example, thorium, uranium, and so on and so forth. And to do so, we had to develop our own counting spectroscopy electronics, which we simply used interrupts on a microcontroller and then accordingly got the data from the scintillator in order to be able to not only identify the intensity value, but also identify the type of component that we have to deal with, so the element that we have to deal with. Into that, there was four steps of calibration that had to follow. The first was to confirm, of course, the inverse square law principle and also characterize and calibrate the sensor to intensity readings, gamma intensity readings from the counting electronics. The second was to take care of some small issue that the sensor had less performance right beneath because of the connectors, the LEM connector that has there, plus some of the interface electronics. So overall, it was a uniform response other than a small cone right on the backside of the sensor. The third step was to calibrate the dose rate response, for which we used essentially measuring the CPS against a known source. And of course, to create, based on the counting electronics, to create the way we specifically measure the spectra for different elements. So for example, cesium, again, cobaltium, thorium, uranium, and so on and so forth, right? You get the idea. Now, having this available at hand, which was facilitated, as mentioned, by measuring the individual interact ports on the microcontroller interfacing the scintillator. Then this allows us to proceed into the goal functionality, which was about deploying the robot without having any prior map about the environment and being able to come back with an intensity map associated with a 3D geometry, and also alongside the intensity map of gamma radiation, pinpoint what is the type of element that creates, emits this field. And we don't make the assumption that we have a single source or multiple point sources. We make the assumption that it's a distributed field and we have to measure it as good as possible. Now, before actually going to the distributed and without point source, we did some work back in 2018 on point sources, where we developed a flying robot that had the same scintillator, and it was able to navigate through several points and accordingly estimate where the source is by means of consensus between several hypotheses about what is the the single point that was emitting the gamma radiation field in the environment. Now, a key problem due to the Poisson statistics is that you have to wait and dwell in theory, right? You have to dwell to get a high confidence measurement. It's terrible flying robots. You shouldn't want to dwell. They have to fly as continuously and span more the area as possible. So back then we didn't do that. Back then we actually dwelled as much as needed. But it's bad because the higher the intensity, the more you need to dwell. That's the idea of the Poisson statistics. So that's actually, I would like to say, really old work in that sense. The second was to build a ground robot which had 3 scintillators, an apparatus that allowed us to calculate gradient directly, since the scintillators were radially distributed on the robot. And this worked better. We didn't have to necessarily dwell equally long, but in any case, since now the motion is slow and the robot doesn't have a major issue with flight with endurance, as flying robots do, here this wasn't really our focus. But this already allowed us to deal with distributed fields. And you see here the robot utilizing this multi-layer map, which essentially for every voxel of the 3D world, it associates mean, gradients, and so on and so forth. And as it navigates, it will be able to do much better estimation of the field, right? So you saw the field with the buckets of uranium there on the left, and then on the other side, there is another cluster. And what the robot is trying to do, but I will give more information in the last phase of the methods afterwards, it's trying to reduce the entropy, meaning the uncertainty of the field of the environment. But both of those were old methods. So let me now get you to what I would actually like to propose. So we wanted to work on very miniaturized systems in order to be able to access from manhole hatches. So this is a robot that is 0.32 meters in diameter. It carries, it does visual inertial estimation. It has a depth sensor in order to be able to build dense volumetric maps. It has the same scintillator that I mentioned in the beginning. It has a relatively collision tolerant frame, not all around, but in most of its directions. And it has a small weight of 641 grams in order to maintain endurance. Now, to focus on the estimation method, these are the key contributions. We don't want to dwell. We want to have continuous 3D radiation mapping. We want to have spectroscopic annotations on every voxel in the environment. And we want the robot to find the path on its own without us having to define an a priori path for covering or exploring the environment. And we want to do so with the idea that it's a distributed radiation field, which means that we're not looking for point source, but we have to cover as much of the reduced uncertainty over the unknown field as much as possible. So there are 2 main modules beyond the classical robot control navigation SLAM topics, which I'm not discussing. These are all based on other work. There are 2 main activities, rad mapping and rad sniffing. Mapping meaning the association of 3D information with the radiation field and its spectroscopic characteristics, and rad sniffing meaning how we plan the motions in order to identify this distributed field as quickly as possible. On the rad mapping, it's a 3D method. Afterwards, I'm going to describe it as 2D, just for simplification, but it's a 3D method. Every voxel of the world at a certain resolution carries the measurements the robot took. And its goal of the mapping method is to not only associate measurements with voxels, that's straightforward, but also predict the remaining of the field. So we can actually make inference about where the robot should go next. And with sparse measurements, cover the whole field under some continuity assumptions. Of course, the inverse square law creates some challenges, how dense the measurements have to be, but that's the core principle. So let me now transit from the 3D representation directly to simplifying 2D representation. So at any current position of the robot, we get the readings from the scintillators, and we will be doing an estimation and a propagation phase. On the estimation, we take essentially all the measurements that we have over all coordinates, and we calculate the mean, and we also calculate the gradient within this voxel, right? So we have multiple measurements within the voxel, we calculate means and gradients. Alongside that, we can now also do binning, and by doing binning, we can calculate the mean confidence and the gradient confidence. So not only the mean and the gradient itself, but also how much certainty we have for the mean estimate that we have at any given time, and the confidence on the gradient estimation. So that's the second step. The third step is that those were only on specific voxels that the robot truly visited. So we now have to propagate over the field. And we need to do a set of propagations. So we go from the voxels that we have measurements and propagate over the remaining field. For that, we have 2 orders, because that's a 3D voxel grid. The way you actually process it, the way you traverse it, influences the estimation you're going to have, right? So we have a specific policy. The first is that in order to propagate means, we make sure that we propagate means only from voxels that have 4 neighbors, or for which we have measurements, and those with priority, and then we go to the next voxels from the neighbors. And then for propagating gradients, we go from the voxels that are linearly independent in terms of their measurements with a simple check. And this allows to propagate the first level and the second level and the third level and so on and so forth. You get the idea as we progress on the voxel grid, and allows to propagate the map. We do this iteratively. Of course, if we propagate only with 1 or 2 measurements on a one voxel grid, all the propagation is largely skewed. But the more measurements we get, the more the propagation becomes much more faithful representation of the reality. And again, there's a caveat, inverse square law, materials that block, of course, radiation. There are many challenges to be dealt with, but that's the core idea behind our work. And on the propagation phase, we propagate the gradient. As we get the gradient, we can also get the new mean contribution of the propagated gradient. And accordingly, we can also estimate the propagated mean over the radiation field. And these are the 3 things that we calculate over the propagation phase. So effectively, we have a mapping module, which the first thing it does, it takes over every voxel all the measurements, calculates the mean. Second thing, with the same measurements over the voxel, calculates the gradient. For these measurements, calculate the confidence for the mean and for the gradient. And after this estimation phase, proceeds to perform propagation by essentially estimating what the gradients of the radiation field will be from the measured voxels all the way to the unknown voxels. And the more constraints you have around you, the more this propagation makes more sense. And this is what the intensity map looks like. So the robot has only done the path that you see on blue, and some areas have been actually measured accurately, like the red areas that you see there. And the remaining is propagated. Now, doesn't mean necessarily this is correct, right? So there could be a weak source somewhere up on the right, or there could be a source that is blocked by certain material. But that's an instance in the propagation phase of the system. So some areas have been measured accurately, the others have been propagated. And what I will explain is that, and I mentioned it, every voxel has a confidence of how much we trust our mean and our gradient estimates, which means that now I can ask the robot which of these voxels is the one for which you are least sure about, should you take a measurement there in order to increase your confidence. Now, before I go into the question I raised, which is about actually planning, for every voxel, we also carry spectroscopic information. And what we did is that we took the characterization, the way we do the counting spectroscopy on our electronics, and then using a linear kernel and a winner takes all essentially approach, we built an SVM, a support vector machine. And at inference time, we take the measurements of the unknown source that we have within a voxel. So we take the measurements that we got inside the voxel, and then we try to match which of the classic characterized elements matches better the measurements that we have inside this voxel. So essentially, is this now voxel that we're taking measurements coming from cobaltium, from uranium, from thorium, or from something else? Or actually, even more typically, is it background? So this is what we do essentially for characterization. And for the phase of estimation, effectively what we do is that we carry a list of how many successful classifications we have per element inside the voxel. And the winning one is the one we attach as information on the voxel. We say now that this voxel is radium. It's not uranium. Sometimes it's characterized as uranium. Some other times it's characterized as cesium. But prevailing characterization was based on radium. So we say that this voxel now dominates in this element dominates in this voxel, and we say that this voxel spans radiation based on radium. And on propagation, we propagate the winning element throughout the neighboring voxels, which also means that we don't only propagate mean intensity and gradient, but we also propagate our estimate about what is the element that gives rise to the gamma radiation field. And now that's the visualization you will have for the same map that I showed before. Now, instead of red areas and green, we have green, which is background. And all those that have some level of radiation estimate above background are characterized with respect to the estimated element that is the prevailing reason for this gamma radiation field. And you see here that all of them is expected to be uranium. And there is a small mischaracterization actually here, which is for thorium. Now, if we have this mapping capability in place, the next logical step to do, or at least from our side, is to make sure that the robot doesn't need us to provide an a priori path in an environment that we might not know beforehand. We might not have a digital twin or a 3D map of some other sort, or not even possibly a 2D map. And we want the robot to enter the environment on its own and perform radiation exploration path planning, which we quickly call rad sniffing, or next best radiation planning, analogous to the next best view problem. Of course, this is in principle a conflicting problem because we want to cover as much area as possible, which means to go fast through several areas. But at the same time, within an area, we actually need to get sufficient samples in order to have an accurate estimation. And it's increasingly difficult with increasing values of radiation due to the Poisson distribution that governs the problem. So it's a conflicting problem. We work in a planning grid, which is not the same as our mapping grid. It's a lower resolution representation. And inside this planning grid, which again is in 3D, we have what we call the global planning, and each voxel of it represents a local planning subset. In the global planning, every voxel is characterized on the cell types that you see on the right. So MIAB stands for measured already, and it's above background. MIBB stands for measured and below background. UAB means that it's unknown at the moment, not fully estimated, but it's above background. And UBB means unknown but below background. And then there are those that are within the range of background and those that are completely unknown. We haven't taken a single measurement about them, and so on and so forth. And the way it will work is that for all those that we know, when the robot is on a voxel that we have characterized successfully, it will want to move away to cover more of the area. And whenever it is in a voxel that we estimate that we are, for example, above background, but we haven't characterized fully, it would like to stay more in there in order to get more measurements about the phenomenon and accordingly characterize it with more accuracy. So transitioning now from this 3D representation for purpose of visualization on a 2D world, I said that, again, our planning grid is a low representation compared to our mapping grid. Inside each of this planning grid, each voxel is characterized as either being measured above background, measured below background, unknown above background, unknown below background, within range of background, or completely unknown. For these four, so those that essentially are above or below background and measured or unknown, but they are not completely unknown and they are not within the range of background confidently. This is where we do a couple of tests in order to understand where we are. The first is a test of if we're in the background area, and this is simple. We have to get sufficient measurement, but after which it's a simple test over the threshold we are in the CDF of the Poisson distribution. If it is above, to check if it is above background, then what we do is calculate the entropy of the measured positions within the cell. Then we sample also some extra points for purpose of calculation. We calculate the entropy of these free space points, and this is an estimate now, that's not a measurement. And we calculate an entropy threshold, which is essentially coming from the convolution of the two. And if the measured one is lower than the threshold, then we say that this is above background in the voxel, right? So this voxel means that it has measurements that indicate that for its vicinity, for its area, the estimate of the radiation field is such that it's above the background for the environment. Now for the within range of background and unknown, what we do is, well, we exploit the inverse square law, which means that the radiation field should deplete soon. So if the one voxel is background, then those around it still, for some of them, we consider them within the range of background. They're mostly influenced by it with a very small distance multiplier called minimum background multiplier with respect to what is the range of this effect. If a voxel now is on background, maybe the neighboring one or the second from neighboring, depending on the resolution, is also in background. So now we are in a path planning that will operate over the several states that I mentioned. Is it on local path planning? Is it on global path planning? So if the cell is measured and above background, measured and below background, or within range of background, this has been good characterization of the voxel. So we proceed to global path planning, and I will explain what this means. If it is unmeasured above background and unmeasured below background, unmeasured above background, it's going to go into local planning. And if it is unmeasured below background, then it means that we don't really have sufficient measurements. And if it's completely unknown, still, this means that we have to get more measurements from this voxel. So in global planning, the idea is fairly simple. We spawn a graph. The graph, of course, only allows us to build collision-free edges. So that's a random graph in the environment. Inside these edges, we find those that actually go into cells that are unmeasured above background, unmeasured below background, and unknown or within range of background. And we go to the next one based on this order. So the best for us is to go to an unknown above background because it's a voxel that actually represents radiation intensity, whereas, for example, going to one that is below background is not necessarily equally important for the robot. And once we identify to which voxel we want to go, we retrieve the Dijkstra path from this graph. And we go to this one. If we're in the unmeasured above, then we want to do local planning. So we are now sitting within this voxel. We also build a graph. We also find collision-free paths only within this graph. And accordingly, we do brute force search and calculate essentially the entropy of the current measurements. And accordingly, since we find which of these areas is the one for which we have the least confidence, we command the robot to go to the area that has the least confidence in order to increase the confidence about the field. So it goes to the area that has the highest resulting entropy. And we take a path for this area of highest resulting entropy within the voxel that we're sitting at the moment for local planning purposes. So I mentioned of the two conflicting goals. Let's try to see these two now in practice. That's a demo of that. So this is a robot. It operates in an environment. We have distributed a set of sources. You see the buckets there on the left and also further inside. And the robot now will start operating in this environment. You see on the right the field intensity, and on the left you have the spectroscopic characterization. And as it will start operating, the blue parts, which you hopefully can see, they will attempt to bring the robot towards areas. We are still in the local planning area because we don't have sufficient measurements. We're operating very locally. Once we get some measurements on some local boxes like here, then the global planning will start to trigger much more. And effectively, you see also the simultaneous characterization of spectroscopic results. So you see the map being updated about it believing that it's uranium, which actually is uranium because the buckets contain uranium ore picked up from a mine in Nevada. And it keeps exploring accordingly this environment. In the interest of time, let me not play all of it. Let me just jump into some steps. Well, actually, let me jump here at least. So now it has got quite some characterization of the field around it. So it progresses through global planning steps into new areas that it has no characterization of the voxels. Therefore, you see it changing the areas that it's going. And the whole idea is that at this point, the mission is pretty much resulting to the field that we actually have in practice in this environment. Of course, if we leave it more time, we can get more accurate estimation. But the core idea is that this should be analogous to the need of spending less time about the radiation field. So now the robot is soon completing its mission. If we let it now to perform more time, it's gonna keep bouncing around in several areas. But at a certain point, the mission becomes less and less productive, right? So at this phase where they have good enough characterization, let me just jump into the end of this. That's actually the resulting characterization. Now the robot is pretty much returning back home. So if we see the map, that's the intensity map that we got. So there were two buckets that you actually saw in the photos and in the video. And this is actually exactly where the locations of the intensity field are presented. All of them based on uranium. There is a mischaracterization of thorium. I don't know if there was actually some thorium in this uranium ore that we collected, but probably not. So that's a mischaracterization, the small amount of yellow cells there on the right, on the left side towards the lower part, but otherwise all of it or most of it is characterized as uranium correctly. If we go to a different experiment where we position different types of material also in a radiation lab. So this is the radiation lab of the university there, and effectively, well, they should tidy up a little bit, but it has a set of sources. So the robot is exploring a set of this office environment, and it will performing the same operation that I mentioned before. So nothing different that happens in principle. It's currently on the local exploration stage and tries to get more measurements around the voxel that it's currently sitting at. The big separation, the vertical, the lines that you see are the lines that represent the planning grid, whereas the small voxels are the voxels that also represent the mapping grid. And the small voxels are linked also with the resolution for volumetric mapping that we use for path planning that you are all familiar with in this video. And you see on the upper side, you see the spectroscopic analysis. Now you see more colors because the robot identifies there are different types of materials in this environment that give rise to the gamma radiation field. And again, the core idea is that this happens without any human teleoperating, either for robot control or for mapping or for spectroscopic analysis. Of course, the data can be gathered for better analysis afterwards, but the whole idea is here is what the robot can do completely on its own during an autonomous mission. And that's a small system, which means we also make sure that everything that takes place runs efficiently on its ARM-only based SBC actually for as long as computing is concerned. And that's the end result that you see. Let me just go directly into the images. This is the intensity map. And this was a rich environment because there were so many different sources in the lab, right? So with some discussion of the people that have stored the sources, the areas are mostly correct. Some of those are not really representative. So the upper part that says cesium, there was no cesium there, or at least so we were told. So that's the upper blue part is wrong. And there are some small flickering voxels that sometimes were yellow or sometimes were red, meaning either thorium or radium. Those are possibly some mistakes, but otherwise the majority of it is aligned with what the radiation officer said about what the elements in the environment were. And this is actually the pinpointing of the actual sources as they were distributed by the radiation officer. All right, these are the publications directly linked with this line of work. And I want to close the presentation with a tangible link again to the idea that, of course, these technologies are technologies that we can now deploy on robots that in the framework of other projects we built in order to be able to explore very challenging environment. And I close again with one of the videos of our work back in August 2020 in preparation for the DARPA challenge, where we test our SLAM methods and exploration path planning together with the animal system from our colleagues from RSL at ETH, demonstrating 40 minutes of continuous, undisturbed, no human operating whatsoever exploration with a system. Followed up, the video will keep playing with an autonomous takeoff of flying robot covering the other parts of the environment and then merging the maps together on the common ground station. And we hope that the technologies for radiation characterization can be combined essentially with this core research in autonomy in order to be able to explore and characterize complex waste facilities that exist around the world, especially in the United States, Europe, and also other places. Thank you.
Thank you very much for the nice presentation. And is there any question?
Have you considered dynamic voxelization?
No. That's we are considering dynamic voxelization now for other work, which means effectively that we are not subject to a fixed resolution, which is a pain. Currently, the work you saw was using hashing. So this means that for a resolution, if our memory is sufficient, we do very quick query, so it's O1. But no, it's a very good point, and we are working on it now, different project.
And secondly, so you said you're doing a winner-take-all categorization in terms of isotopic identity. Is there any reason not to preserve the relative weights of the different isotopic candidates and then individually propagate those from the known data?
Not in particular.
Okay. Do you think that?
So I can see the benefit of doing it in the sense that, especially if we have 99 estimates versus 1, it probably is what we're doing is okay. But if we are at the border multiple times, the propagation can help. Absolutely valid point.
Right.
Yes.
Consider a lot of requirement on radiation. Your vehicle plan for addressing using vision-based SLAM, right? So you try to establish the environment at the same time. I would consider combine those two different kind of goals together. So one thing is radiation, but also on the other side, try to map the environment.
Yeah, so from a deployment standpoint, we have done a couple of missions that we first use plans like the ones you see here. They just do exploration based on, for example, the frustrum of LiDAR or vision whatsoever. And then we can follow up from a radiation planning standpoint. But actually, as long as the robot is, eventually what we found is that as long as we only plan within the explored space, implicit exploration takes place in any case through radiation mapping. It's not ideal one, but we also don't have to sequence the two missions. So if we were to do a single one, we'll be doing what we just showed. If we had the privilege of time, we'll be doing an exploration mission, taking them up, and then planning a priori.
Yeah, that makes sense.
Yeah. Yes?
So I noticed in your presentation that you are using a multi-channel analyzer with 32 channels.
Correct.
I wondered if it does not limit your ability to identify the isotopes.
Yeah, so of course, the more you have, the more resolution you have, right? But I think the key thing is that the signature of every isotope is pretty clear. So there are two aspects. The first aspect is we aggregate more measurements. So although we don't dwell, we still aggregate measurements within the voxel. So your question it's actually very relevant to the first question that I received, which is if within this voxel that you are, there are actually 2 or 3 elements, does your method work equally well given the resolution you have? And the answer will be no. So we actually kind of make the assumption that within the voxel, there is one prevailing isotope. Otherwise, more channels, smaller voxels.
The other thing, you were saying that you are comparing the values with some background level.
Mm-hmm.
How do you know what the background level is?
So we do the background. So in the beginning, at deployment time, because the background is not really always one, right? So at deployment time, we make the assumption that what we gather in the first seconds is representative of background. We store this value and we progress with it.
Okay, thank you.
Thank you. Yes?
On the radiation mapping front, when you're adding these measurements to your system, do you have to batch solve your entire history of measurements, or you can literally be out single measurement you occur.
We do batch of the voxel, which is it's batch, but it's a very small problem. Then we only do iterative update of the propagation phase. Thank you. That's it. Thanks a lot.
Okay, thank you very much. So our first speaker from the afternoon session is Fabio Bonsignorio, and is a professor and HERA chair in AI and robotics, and now is working in the laboratory for autonomous system and mobile robotics at the University of Zagreb. And I had the opportunity to work a lot with Fabio. He's the chair of the technical committee in benchmarking, teaching BEBRAS in benchmarking and for robotics research. And like, I hope he can hear me. Fabio, can you hear me? We cannot hear you.
Yes, yes, I can hear you. Also
Okay, now
see
we
you.
can hear you.
Sorry,
That's-
but I am a bit dark, but
It's okay, it's perfect.
try to
Fabio, thank you very much for
get a
waking up
bit
so
of a
early,
visual to see. Okay.
for joining us, and please go ahead. Yeah.
Okay. Good afternoon, everybody. I'm happy to be virtually with you. Today, I'm talking about the issue of reproducibility and benchmarking in general, and in particular in application in the context of nuclear decommissioning. So we know we are in a moment of in the development of robotics, where thanks to a few progress in IoT, machine learning, and AI, we basically have the possibility to develop much more application than it was possible in the past. For example, in the past, it was almost impossible to have workers interacting very closely and also physically with robots. Now we have even the possibility to have to wear robots. Now, so this means that thanks to a number of progress, we have the possibility to have a bunch of new applications, and it is quite natural to use this kind of systems also in areas where the activity of humans is less advisable, no? Because because the environmental conditions are not particularly suitable for humans. This is even an application that unfortunately we are seeing every day, even for military application, which is a typical example of dangerous activity that humans don't want. Unfortunately, we were still discussing if this kind of application is legitimate when it became a kind of standard tool. So that said, despite the fact that we are having a dramatic improvement in robotic technology, this is not without problems. Now, I think you remember the DARPA Robotics Challenge 5 years ago, when basically what we have, I think to many it was a surprise, no? The fact that the best robots that are available for us have actually problem in performing. You remember that some of the main tasks of the DARPA challenge. One was opening a door and entering a room without falling. another was operating a valve, another was sitting in a car. And you remember, and the situation has probably improved, but not so much. The success rate was about 5%. But what was even more relevant is that a study was performed in the background, a kind of societal study that has shown that an average of a little bit more than 10 people was teleoperating those robots. So that was the state of the art 7 years ago. On the other hand, despite the fact that we are very happy because our field is growing very fastly, this is a Boston consulting forecast of a few years ago, and it foreseen about 10% year of a little bit less than 10% year-over-year growth of the whole robotics application. This is actually the real numbers. Now we are in 2022 are much better. So it will probably be closer to 15%. So robotics is very healthy. It's a growing field. Applications are growing. Industry is growing. Of course, research has more funding. But still, if you compare the 80 billions of turnover of the robotics industry to the global gross domestic product is still 1,000. So why? So one of the reasons could be the fact that we still, when we report research, but also when in a certain sense, also when we perform it, we might be affected by what many years ago we dubbed as Lukma no hand syndrome. No, so a big problem that we have with a lot of research is reproducibility. So is it possible? So if you look at a typical journal paper, not all the times, I would say many times, if not most of the times, there is not enough information to repeat the experiments. And this means that many times you have a kind of beauty context. No? So you have had a good idea about an application, a good idea about an algorithm, and you show something nice. For example, a humanoid robots doing parkour on a video on YouTube. Okay, this is noticeable. So this is remarkable. This means that there is a real progress. But if you see it from a point of view of understanding the state of the art, to know what we can do and what we cannot do, and which applications are feasible and which are not, this is a problem. And it is a kind of a systemic problem in our community. So we really have an estimate of a state of the art. The community has been really aware of it. I think that almost everybody agrees, or many people agree that we have this problem, and this triggered already many years ago. I remember that when we started the special interest group on good experimental methodology in Europe at EUROM, which was at the time the big research network in robotics in 2008, so almost 15 years ago. And there has been many workshops on this topic. We had in 2009, we had the technical committee PBRAS, Performance Evaluation Benchmarking Robotics and Automation System, was founded, and we did some progress. Since in 2015, we had the first ever special issue in ITIR publishing venue of paper pretending to be reproducible, aiming to be reproducible since 2017, so 5 years ago already. The Robotics Automation magazine, and to my knowledge, it is still the only one, allows to publish reproducible articles, which, and I will tell you what we are talking about. So I was talking about the DARPA Robotics Challenge, which was a little bit more than 5 years ago. We all remember the dramatic events of Fukushima also, but they were also dramatic about to a much less extent for robotics, for the robotics community. So we, at the time, so Japan is probably still leading. It's definitely a place where robotics is well known and widely practiced, both from research and application standpoint. So everybody was waiting for the robots going into to the rescue in Fukushima, but this didn't happen. So this, luckily today the situation is better. No? So we have a number here. Is a list taken from a science article. So we have a different shape robots that can be used in a radioactive environment. Of course, when we talk about decommissioning, we are not talking about search and rescue in the middle of a disaster. So we are talking about situations where the level of radiation is acceptable. However, why this is related to the discussion about reproducibility and benchmarking? Because it's like in other areas. So in other areas, because we routinely use robots for welding in manufacturing lines. We are researching about a robot for home assistance, or we are there is a lot of hype and significant progress, but less fast than expected by many in self-driving cars. So even decommissioning is a kind of disassembly task, and nuclear decommissioning is a disassembly task in an harsh environment. Harsh for the electronics, for the signals, and so there are ways, you know, these are some about, but typically a radioactive environment has negative effects on how the robot works. You have changes in the electronics. Elastic materials become more brittle, but all of this is actually manageable, no? Because you can define procedures, like in this paper by Zhang and alias. You can actually create a procedure to see you also have various solutions. One is, even if the level of radiation is not so high, is even to replace components when at scheduled times. But this requires because basically we are talking about something that is enabled by this second wave robotics revolution that I was quickly quoting before, no? Because if I have many sensors, if I have force control, and if I have some pattern recognition capability coming from the progress of machine learning or deep learning, and if I have the possibility to create some plan, some kind of AI that we can use safely, you can use robots for deconstruction, not just so to disassemble. So actually, the kind of technologies that have been developed in construction robotics, still a niche, but I think a potentially very impactful niche can be used to this purpose. Of course, if we talk to good old-fashioned, so the kind of nuclear plants that you want that we wanted to, that now it is needed to decommission, to dismantle safely for humans and for the storage of material and so on and so forth. Those plants were designed for humans, so that we could think to use humanoids robots, no? Because all our working environments, including nuclear plants, have been designed for humans. No, it's just now that we could seriously think of when we design a factory or even an hospital, to consider by design that some robots like those that we have seen before in the science summary will be used. Most environments have been designed for humans. So it would look natural to use humanoid robots for this kind of applications. However, we have quoted before the DARPA robotics challenge, but in general, the problem is that if my machine has some level of autonomy, at current stage, I have problems to guarantee that it will work most of the time. So maybe we don't expect that an autonomous, a semi-autonomous robot, semi-autonomous robots works 99.99. So we don't expect a 6 sigma in terms of reliability, but at least we should have a 99% to make the usage safe and competitive with humans. Of course, in the context of a environment which is aggressive for our biology, it is better to send a robot. But the problem is how much we can trust the robot. So the first thing that I need to be able to do for a robot to assess the reliability and safety of a robot is to be able to repeat experiments. No? So you say that your robot is able to operate to remove a screw from a wall, a big screw from a wall, or to cut a piece of concrete. The first thing that I need to do, but this years before I have a robot, and a robot in the field, I need to be able to reproduce what you claim. No? So this is actually, it's the cornerstone of a scientific method. No? A scientific experiment is an experiment that your colleagues can reproduce. This in robotics has not been, is still not mainstream, so is still not what you can do all the time. I think this is due to, so I think many think this is due to the fact that an article is a description. If you describe the pendulum experiment by Galileo, so it's quite simple. If you describe an experiment on a robot, so the quantity of information that you need to convey is much bigger. So the pendulum example, it's an extreme, because it's old science, is science of centuries ago. But it's still, I hope there are not too many physicists there, but still, even if you think to experiments on high energy particles, they are still kind of well structured. You have two beams of protons, and I mean, it's still, in the case of robots, the more autonomous they are, the more complex becomes the situation, in the sense that you need to give more information to be able to create the same experimental condition. So what is a reproducible article that since 2017 you can submit to RAM? It's first of all a descriptive part, so you describe the experiment, and this is quite similar to a traditional journal paper. But then you will have to give in some form, can be GitHub, can be code option, can be IEEE data port. You will have to give the data sets that you use it to perform your SBAM. And then we will need the code, because basically most of the information is in the code in a robot, more than I use it with algorithm, yes, but how you implemented it. And then the hardware. So the code not necessarily has to be the source code, but has to be the real code. And the same for the hardware. Not necessarily it has to be an open source hardware. It can be a widely used hardware, or in any case, you need to tell me which version of, for example, Pepper you use it for experiment. And this happens, so it's interesting to see that, for example, this is an editorial from Nature Machine Intelligence that actually assess that in the year of our Lord, 2019, the robotics community started to think to the scientific methodology. So what's the problem? No? So the problem is about metrics, because I will metrics and statistics. I would say that there are two main things that we tend to forget. One is the fact that really the basic, the ground level fact that if I did if I do a claim, so this robot will be able to cut a piece of concrete most of the times, I need to, first of all, you need to be able to build my robot, or to buy from me my robot, and to cut the piece of concrete. And the second important point, which is also, I think after reproducibility, that we can say it is somehow, at least you have a place where you can send a reproducible paper, the Robotics and Automation magazine, but you can self-constrain yourself to report your work in such a way that can be reproduced. The next stage, I think, is statistics. So how many times, depending on the changes in the environment and the robot configuration, it will be able to perform a task, and how the time to perform a task will change depending on the configuration of the robot and the environment and the task. this is something that we are just starting to approach. So because basically it's complicated. So to approach this problem in general is not obvious, no? Because if you think to how the robot can be shaped, and there are many possible shapes, which kind of tasks you can perform, or and in which environments you can perform those tasks, there is a huge variability. So this suggests to create benchmark on a case-by-case basis. So first of all, it has to be reproducible, but then we need to be able to measure the results. I think we need some kind of ontology, but I also know that ontologies have been not very successful in the past. No? That's why I say maybe we need a bottom-up approach. So just let us create a benchmark for cutting concrete or for removing screws. But it's possible that we needed to develop some kind of ontology. And one of my, since this is a workshop, I want also to do some speculation. One of my suspects is that the fact that we don't measure objectively, in particular, the probability that a task is correctly performed, and the fact that we cannot reproduce results is somehow hiding to us as a community some real big problem in robotics. One of that could be that we would need some kind of, I know this can be controversial for some, but some kind of very high level ontology that maybe it is could actually emerge from the activity of a robot. But I think, for example, to compare two different robots doing the same thing, one with 5 joints and another with 7 joints, you need some idea. No? So I think that the driving point is how well it performs the task. But then you need to describe objectively what are the tasks. And this, I think, requires some formalization that we still don't have. The other, so I was talking about statistic, and I think this will be the last important point that I wanted to quote. So I was saying, first of all, it should be reproducible. It should be measurable, but what should be measurable? So the point is that until the robot performs a very repetitive task, so until the robot, it's far from what we usually expect from a robot. Statistics is not, so no, it's important, but it's also easy. Think to a welding robot or an assembly robot in a traditional car factory. So you have a median time between failures, which is around 8,000 hours. No? But this can be measured because this is always the same kind of trajectory. As soon as you have deconstruction, you have every plant that you want to deconstruct, to decommission is different. So you need to be able, that's why I was quoting ontologies, no? But not necessarily, you can stay very close to your application. But then you need statistics. So how many times if I put my robot in a new environment, it will be able to map the environment. This is something that need to be given. The purpose of this slide is to show things that we know, that p-value, there is a long discussion about p-values in other communities, but we rarely use give a p-value to validate our claims. And if you look on the other side of this slide, you see how in other fields, in medicine, clinical research, really there is a huge number of well-defined kind of a way to perform a statistical experiment. My opinion is that we need to go in that direction. Then we have some, we already have some reproducible article published. They follow this common sense rule. Now we haven't the time to go into the details, but the nice thing, nice or bad things is that if you check a sample of journal papers to see if they follow, these rules, you will see that most of the time they don't. Where we are here. So and then I finish. So we have a few published reproducible articles. So article giving you description, clean, nice follow description of experiment following these guidelines, which are basically common sense, like clearly state the hypothesis, clearly state the objectives, clearly say what you are measuring and what you are not, and things like that. And then they give you either hardware identification, data sets, and code. Then we are still waiting, as far as I know, to see a short article, because the nice thing about this reproducible article is that you have a review of the article, but then the real review is expected to come from the community performing the same experiments using your data and checking if they can be reproduced. And these are what we call the R-small articles. So a short paper that have the dignity of can be published on the Robotics and Automation magazine, where you say, I did your experiment and it was almost correct. I found this that didn't match with what you claim in your first article. And then there are also the possibility for the authors to do another short article to say, no, well, to explain that maybe the people reproducing their work, they're doing something wrong, or to say, yeah, you are right, we should also have considered the color of the light in the room, we didn't, and that affects our performances. We are at the first stage, because so far nobody wrote a small article. So, I think that it could be interesting for people. So, it could, for example, some article. For example, there is a planning semantic navigation article among this small group of capital R articles that can actually reproduce it in a very short time. So it could be interesting for some of you to reproduce it and maybe submit to see, to trigger, because the idea is that the one thing is the peer review, that it's in part a guessing work, but the real review should be over the time people reproducing the results. That is nothing new, no? It's what traditionally we call research. So so the relation, I think that the real importance on these issues, reproducibility, benchmarking, and estimate of probability, just of a bare probability to perform a task, it becomes more and more important as you ask for more complex activities. And if you want to do, unfortunately, activity of like disassembly, deconstruct a building or a plant, a technical equipment, a complex technical equipment requires a certain flexibility and adaptivity and some level of autonomy of a robot. Of course, you may, most of the time you still use teleoperation but still, even in teleoperation, the variety of the task and the condition where the task is performed change. And this immediately creates the need for statistics. I think we really needed to consider. I know people don't like to do this because if you have to do 100 experiments all the same, this requires much more time. But this kind of information is needed. An aspect that also it's randomization. So how, because it's not as if you can do 1,000 times the same thing, probably it will work always the same way. But how you create a sufficiently different experimental condition to feel safe when you go to the field. This is so we need good models, we need extensive tests, and we need performance models. So it's not rocket science, nothing that we cannot do, but something that I believe we should started this activity with a good experimental methodology interest group in Neuron. It was not very common that people share the code and data. Now this is widely done, not always done. It's not exactly the same thing as saying that so the fact that you share code and data set doesn't mean that you have shaped, designed your report as a reproducible report, and doesn't guarantee that your experiment was organized as what matters more than the report. That it was designed as a reproducible experiment. So what to conclude, what I want to say is that really what makes so I don't think we are bad people who, as a community, but we don't like to do reproducible research. So we don't like to be controlled by the colleagues. No, I think that it's more that what we do is very complex. No? So a robot, it's not a pendulum, and this creates problems. What makes more urgent the need for reproducibility and benchmarking is actually the fact that you need more autonomy. So if you go in an activity, so if you have to assemble a car, it's more easy to understand what you have to do. But if you have to disassemble the car, or if you have to disassemble a technical building, like a nuclear plant, whether there is radioactivity or not, it becomes something that needed to be measured. So the possibility to do what you aim to do needed to be measurable in terms of probability. And that's all. Thank you.
Thank you, Fabio, for your presentation. And do you have any question for Fabio from the audience? Maybe I can start with a question, Fabio. So I'm wondering, you show a lot of like video, and I appreciate a lot of the work that are you doing for the community, but you show a lot of video where we see a lot of hardware failure, right? So, and in the last year, we can say that the software has been progressing like very quickly. So we have a problem known for that we have a problem with the hardware. How do you think you can make up? I mean, you discuss about also reproducible hardware, but is this not too difficult to do?
No. I don't think it is to do, as told before. No? So actually, the dramatic failures of the DARPA challenge were actually with very complex robots. No? So it's true, it was operating Evolve. No? But you can operate Evolve with a much simpler robot than a humanoid robot. No? No, I don't think okay, hardware reproducibility has different aspects. Now, if you think to the electronics, it is mass-produced electronics. It's always the same electronics. Reproducible, the hardware of a robot can be that either you use the same model of robot or you open source the design. I don't think this is difficult. So it's something that can be done by typically still is not done as often as it would be advisable. But I don't see any because what the reason why this the necessity to benchmark and to have statistical significant and reproducible results is important is that what you do if you see that the humanoid robots cannot be used. Okay, you will build a wheeled platform with an arm and a simple gripper. No, this is the reaction of the engineer is okay, that's too complex, it doesn't work. But I also want to use the very complex robot because for some application could be better. And how I can do that? So how I can use more flexible and more adaptive robots? I think that, of course, there are technical issues that you need to solve, but also it's a good practices could help, because if the more flexibility, the more unpredictable becomes your robot. But I don't see any real barrier. I think it's more an habit that we have than a real big thing that we can do, because in the end it's not even so complex. No? So you store the data.
Okay, thank you. And do you have any other question? Please go on the microphone here in the front. Should be on. Please on. Okay.
Hello, can you hear me?
Hello.
Yeah.
Yes.
Thank you, Fabio. Well, first, thank you for pushing that subject for all these years. As you said, I guess despite all your effort and the ones of the one of your colleagues, there doesn't seem to be that much progress in that area. And you talked about the reproducible articles and those things which are essentially harder for us to get in. I guess my question is, how do we bring more incentive to push people to do it more? I think there are answers on the negative side where we could say, well, you sort of sanction if you don't do it, but how do we bring something positive to really encourage people to actually do that effort?
Good point. But one of the tools that I think could help is to give dignity to the mere reproducible reproduction of the results. No? But this is what we do on the Robotics and Automation magazine with small articles. So if you take one of the published big articles, so the article that have been accepted because they are supposed to be reproducible, because they give you code and data, etc., and you run again the same experiment, and you format it as a short paper, you can publish this. Because I think that so it's one of those situations in which you need an investment that will benefit the community, but when everybody will start to work in that way, no? Because where we lose a lot of time when a student, for example, or a researcher start a new work using the algorithm published by someone else, typically wastes a lot of time because the information is missing. The idea of a lot of too much information is missing. The idea here is to ask the person doing the initial work to invest a little more time so that the myriad of people using, or the many people using his work or her work will save a lot of time. So for the community, the cost of making results reproducible is largely offset by the fact that then everything becomes easier. I think a tool is this one, to give dignity to the work of reproducing work. I think this is what we have done so far. I think it's really a cultural habit, no? So the fact that you try to attract their attention by doing something new and strange, while if someone else just do what you already did a little bit better, this is not as appreciated and it should. So this is at the level of the reviewing papers. Probably we should also value more the significant increments, no? So, but I think that having shared the benchmark, which is not the case in many application domains, would be another important trigger. So allowing to reproduce results, I think, is just the first step, because the other one is benchmarking. If you look at machine learning or computer vision, the fact of having benchmarks have really forced a much faster advancement. But so let's write sensible benchmark. So.
Okay, thank you. Thank you very much, Fabio, for joining us today. It's very early for you, so I really appreciate it. And yeah, if you have any question, you can log in on the Zoom, and if Fabio doesn't go sleep, he will answer. Thanks, Fabio. And now let's continue with the second part of the contribution of this workshop. So the first speaker cannot join online and is not here, so we will play a video for him. If you have question, you can contact him on his email. So please play the video.
Hello everyone, my name. My name is Darby Schepper. I'm from the Department of Mechanical Engineering at the University of Leuven, and today I will give a brief presentation about our work entitled Design and Comparison of a Passive and Active Multiple Radiological Point Source Localization Algorithm. Let's first start with a quick introduction or a general context of where this research is situated. Data shows that in Europe a series of nuclear power reactors are reaching the end of their operating life due to the fact that old nuclear power plants are being replaced by newer plants. On the other hand, there are also plans for nuclear power phase out towards other energy resources, and also a lot of power plants are entering a decommissioning phase, as can be seen on the left figure, and as a result of this, D&D activities will increase in the coming years. At this moment in time, radiation protection officers are in charge of performing the in-the-field measurements. However, there are some severe drawbacks related to this task, such as the high potential dose rate that could occur during the measurements. Besides, manual process of data acquisition is sometimes very time-consuming. Therefore, a high demand towards semi-autonomous robots can be observed. On the one hand, new robot design arises with large flexibilities and radiation hardened electronics, and on the other hand, new research like this one focuses on algorithms that are being developed for fast radiation mapping and source localization. This work basically developed two algorithms for multiple radiation source localization. The first one is a passive approach, where a robot scans a measurement pattern independent from the already acquired measurements. And the second approach is the development of an active localization approach to localize point sources based on the history of previous measurements. Therefore, this approach can be used online and does not rely on a pre-gathered dataset. So the first approach is a passive approach, as can be seen in the figure. So the first step is the gathering of a dataset containing sensor data and positions where a measurement is sampled. Next, the radiation or the background radiation is determined. The next step is to perform a Gaussian smoothing on the sensor data to reduce the noise of the inverse distance weighting interpolation approach in the following step. Next, we amplify the local maxima and normalize the intensities of that matrix. Therefore, each individual intensity is mapped the same. And the next step is to search the amount of sources available in the environment using an iterative k-means algorithm. And finally, the locations of the found sources with their intensity is being calculated and optimized using a gradient descent algorithm. On the other hand, the active source localization approach is structured as follows. So in contrast to the passive algorithm on the previous slide, the active approach doesn't use a pre-gathered dataset. The routine starts by taking an X amount of initial random measurements over the entire state space, and using these measurements, a thin plate spline interpolation is used because of the scarcity of the measurements. The interpolated data is then used to create a belief and penalty matrix. The belief matrix is a matrix of positions of which the highest probability corresponds to the largest belief of a possible source, and a penalty matrix penalizes the positions where a measurement is already being sampled. And by combining these two matrices together, a new measurement will be taken at the maximum of that combined matrix. This procedure is repeated for an amount of times, and then the next step is to calculate the position and intensity of a single source, and the influence of this source will be removed from the existing measurements. And if one of the stopping criteria is met, the algorithm will use the same procedure as in the previous slide to optimize the position and intensity of the found sources. To validate the two approaches, a series of simulations and in situ measurements were performed. For the in situ measurements, we used 3 point sources, an industrial detector, and a 2D linear guidance system to simulate an actual robot scanning an environment. So as can be seen in the two pictures, the active approach needs a lot less measurements to localize point sources in an environment. So a reduction from 324 to 48 can be achieved. And as we can see by the results of the localization accuracy and intensity accuracy, both approaches have a similar accuracy regarding localization and intensity estimation. However, the passive approach scores a bit better regarding location estimation. But on the other hand, as can be seen by the execution time, the active approach scores worse regarding the time needed to localize sources in the environment. So now let's conclude this presentation and give some tracks for future work. To conclude, our algorithms can localize point sources in a quite accurate way. So the benefit of the active approach is that a large reduction in measurements can be achieved. However, on the other hand, the active approach results in a rather large distance to be covered between the measurements, and this results in a longer time needed to characterize an environment. So tracks for future work concern the optimization of the active search framework in general and in terms of time. Furthermore, we would like to exploit Bayesian techniques for active sensing or active localization. And lastly, we plan to perform in situ measurements in larger areas where a mobile manipulator robot can be adopted. Thank you very much for your attention. Hello everyone, my name is Darby. I'm from the Department of Mechanical Engineering at the University of Leuven, and today I will give a brief presentation about our work entitled Design and Comparison of a Passive and Active Multiple Radiological Point Source Localization.
Okay, I'm sorry for that. So unfortunately, he couldn't join, but if you're interested in his work, you can send him an email. And the next speaker is Lorenzo De Mari, and he's joined online. And he will talk about the nuclear plant containment building inspection via by a long reach cable driven hyper-redundant robot. Are you there?
Hello, can you hear me?
Yes, we can hear you.
Okay, good. I'm going to share my screen. Can you see the slides?
Yes. Yeah, it's perfect.
Okay,
Please go ahead.
good. Okay, thank you very much. Good afternoon to everyone. I'm Lorenzo De Mari, and I'm going to present the abstract that Angela just mentioned. I want to mention also the other authors before starting. They are Alessandro Pistone, Daniele Ludovico, Darwin Caldwell, and Carlo Canali. So we are talking about hyper-redundant cable-driven robots. Just have a look at what they are. They are robots that are, of course, hyper-redundant, which means that they have a number of degrees of redundancy, which is greater than 2, and it allows them to move in harsh and narrow and constrained environments. And of course, they are also cable-driven. The cable actuation allows to separate the actuators from the joints and to move them in the chassis at the basis of the robot. This opportunity makes actuators safe from any kind of danger that could be present in the workspace, like, for example, very high temperature or very high radioactivity level. And moreover, it allows the arm, the robotic arm, to be very lighter, and it increases its payload capabilities. For these reasons, these kind of robots are very suitable for industrial site inspection. So, given this brief introduction, I want to present to you SLIM. SLIM is a snake-like manipulator for inspection and maintenance, and is shown in the picture of this slide. We can see that the robot is composed by 4 elements. The first one is robotic arm, which is composed by 12 revolute joints, which all have a rotational axis parallel one to the other, and therefore the robot is planar, is able to move only on the vertical plane. The second element is the actuation box, which has an additional degree of freedom, which is an additional revolute joint, J1, and also includes all the actuators that drive the joints of the robotic arm. And we have 1 actuator per joint. Then we have a robot base, which is the structure placed on the floor in the picture. And finally, we have an end effector device. I want to point out that this end effector is just a prototype that was mounted for another kind of purpose. Therefore, this is just an example. So here we can see each module, the details of the module that composes the robotic arm. And we have a rigid link made of steel and a joint, which is, of course, revolute, as I already said, and is composed by a pulley, which is driven by a cable made of a synthetic fiber, which is called Xylon. And the angular position of the joint is measured by an absolute encoder, which is shown here in this CAD. So here you can see a brief video in which you can see Slim and also some colleagues of mine. We can see here Slim in its parking configuration, which is rolled around the actuation box in order to occupy less space as possible. And we can see that it is able to unroll itself completely in order to perform any kind of tasks. The length of the robotic arm is more or less 4.8 meters. So the idea of this abstract is to exploit SLIM for the inspection of nuclear power plant containment building. In this picture, which is not to scale, of course, is just an idea. We have SLIM attached to the wall of the containment building. And from this position, the idea is that the robot moving inside the room is able to perform some kind of inspection tasks. For example, radioactivity measurement or pressure measurement and so on and so forth. But of course, depending on the end effector that is mounted on the tip of the robot, it is possible also to perform some physical tasks like pick and place of some elements if it is required for any reasons. Since the robot is quite short, it is as I already said, almost 5 equation, is that in the wall of the containment building, there is a moving platform that is able to bring the robot around the building so that it can perform its inspection task in the whole room, let's say. So having these characteristics for being used in a functional way to inspect a containment building, the robot should be a little bit improved. In the first part that should be improved is the design, which should be a new design that is that allows the robot to move in the whole 3D space, and also to increase its workspace size, because 5 meters is too short for a big building as a containment building. Moreover, the control strategy, which is not explained here in this presentation, but is shown in another paper that you can find referenced in the abstract, should be improved in order to prevent vibration and drifts that are all caused by the cable actuation. And finally, some components of the robot should be replaced with radiation tolerant components. The presentation is finished. Thank you for your attention.
Thank you, Lorenzo, for your presentation. And do we have any questions, please?
Yes, are you collaborating with any plant operators?
I'm sorry, I didn't get it.
Are you collaborating with any NPP operators?
No, right now, no. The robot was designed for the inspection of industrial sites, which are not nuclear power plants. So it's just an hypothesis without any kind of collaboration for now.
Hi, Iain Darby here with a question, if I may, Angela.
Yes, please go ahead.
So, sorry, I'm late joining, still quite early here. Hi, Lorenzo.
Hello.
Just following up the question that was asked there, if you've not been to see a site or see it inside, I think the premise of how you think you're going to install it, I would revisit and reconsider. The idea that you're going to have it fixed on the inside of the wall. I'm just thinking about the decommissioning. We'll get similar projects where the decision is to install a robot arm to do some decommissioning. It's not permanently fixed this side. One of the major challenges is where and when to locate the vehicle or a robot arm as it comes in. You can have quite some distances, and your suggestion is going to drive an awful lot of other maintenance and infrastructure for a robot arm.
Okay.
When there's lots of other things, cranes are pretty common. There's tracks in the floor that they could install that would move things in and out of the way. If you've not been in contact with anybody and have an idea of a site, but I would encourage you to go and maybe try and make contact with one of them. And I think the design of the arm is very interesting, but I think at the moment your working premise of where you will install it and how somebody else will use it probably needs further thought.
Okay, yeah, for sure. Thank you. Can you hear me? Can you
hear
me?
Yes.
Okay. Okay. Thank you very much. I appreciate it.
Okay, I think there are no more questions, but if someone has question can log in on the Zoom and write. I think Lorenzo will stay for a while. And
yeah, for a while.
Okay, thank you very much for joining early.
Bye.
And, now our next presenter, please. So our next contribution is about viewpoint presentation for teleoperation of robotic manipulation in fuel debris removal task with 3D dimensional obstacle, and will be presented by Mr. Liu.
It's very honored to be able to speak today. Today I'd like to talk about the representation in optical environments. And after the systematized department acted in March 2007, two visual mappings that have solved and because of high level radiation, we have entered the and directly. So
Pardon? Can I see? Okay, okay. And currently the efforts are underway to decommission the plant, and the television is considered as a method of the decommissioning in terms of the protection of the human operators. But the problem is that the efficiency of television is relatively low compared to the on-site work, and the main reason is considered as the relatively low. Okay, sorry. The main reason is considered as the lack of the visual information. So there are two previous research. The first one is a multi-camera system in the teleoperation, and Kamezaki and others proposed a 6 cameras system to provide more visual information. But the weakness of this research is that the multi-cameras can increase the cognitive load on operator because there are so many monitors in front of the operators. And there are second research, which is the placement of the single camera system in the teleoperation. They also proposed the optimal and allowable viewpoint of digging and releasing tasks by conducting subject experiments. But the disadvantage of this research is that the study only focused on the flat areas. So in this study, the objective of this research is to propose the techniques for viewpoint presentation in teleoperation under the obstacle environment. And next, I would like to introduce the experimental methodology. Here we have 5 members of our research group with no teleoperation experience, and Panda are manufactured by Frank Amica is used in the experiment. The task is grasping, and after the experiment begins, there is the verbal instruction from the robot operator to the camera operator. So the camera operator can follow the instructions to change the parameter of camera, and there is a video from camera to there's a video from camera to send to the monitor. And the robot operator is asked to sit in front of the display, and the operator can use a joystick to control the movement of the robot arm. And we have to declare that any under circumstances, the robot operator can only receive the visual information from the monitor. And the action of camera is the change in tilt angle, in pan angle, and the camera can zoom in or zoom out. So and next, I would like to provide some specific information. So the picture in the upper side is the reconstruction data from TEPCO, and we built a 1/7 model using cardboard, and we assume that the shape of the field debris is a normal distribution. So in addition, as shown in the figure below, we made some sticks and obstacles to make a shape to make the model similar to the fallen structure components of the plant. And we use some pebbles and name cards as the target of the grasping task. So the result is that through the trial and error in the experiments, we consider that the television can be divided into 2 phases. Okay, in the first one is the approaching phase. In this phase, the robot arm moves to the vicinity of the target. And in the second one, the target grasping phase, the robot arm grasps the targets. And during the experiment, there are 3 problems confronted in the experiment. The first one is the difficulty in understanding the movement in depth direction of the monitor like this. And because the operator is difficult to understand the depth information, so the collision happened multiple times during the experiment. And the solution to this problem is we can representing the viewpoints that perpendicular to the direction of the movement of the robot arm. So the human operator can see the movement of the robot arm very clearly. And there's another problem is that if the robot wants to grasp the target, fine-tuning the position of the gripper to the graspable range of the target is very time-consuming, and which is considered, the reason is considered as the operator cannot perceive the environment precisely. So we can provide the top view and the side view multiple times to improve the, to help the operator improve the environmental perception. And to conclude this, research, so the try and error in the experiment, we consider the calibration can be divided into 2 phases, and we propose the visual viewpoint presentation techniques for each phase. And in the future, we want to improve the depth perception of the robot operator using a single display and providing suitable viewpoints for the grasping task under the obstacle environment. Okay, thank you for listening, and I can will receive the question.
Do we have any?
So the visual feed that the test subjects were operating from, was it just a plain camera feed, or does it include any sort of assistive markers for them?
Okay, so so may I confirm the question? So you mean the visual information only includes the plain information where there's other information provided by the system?
Yeah, is there any markers or other information
no, actually,
into
no,
the feed
there's
to help
only
them?
visual information provided by the camera, so there's no markers and other instructors.
Okay, thank you.
Okay, thank you very much.
Hi, so you spoke about the problem of depth perception with the flat screen. Did you also consider to use VR goggles?
Sorry, could you repeat your question?
Yeah, you spoke about that there's a problem with depth perception if you use the flat screens.
Yes, yes, yes.
So if you use VR goggles, like the virtual reality ones, then you have depth perception.
Okay, so
did you consider it?
Yeah, actually, so yes, it's very thank you for your valuable comments. But yes, I think I will consider this in the future. But I also have read some research about using VR that they can provide the binocular parallax, which is considered as the main the main system of the depth perception of human beings. But there's shortage of the using VR devices because so making the VR system that can provide depth perception is very difficult, and human cannot use these devices in a long time. And so if we want to use this kind of system in Fukushima decommissioning project, we have to consider some system practical. So, and currently actually in the construction site, the multiple display is used. So we'll consider a practical way to do this project. So that's the reason why we choose the single display. But thank you for your comments. We will improve this research in the future.
Thank you for your answer.
Okay, thank you very much for your presentation.
Thank you very much.
And I just want to make sure like the next presenter is not joined yet. So I don't know if she will present later, but after we will have our 3 speakers. So I know we are late a bit, but let's have a coffee break of 10 minutes. And after we will come back with other 3 talk. And I'm sorry for the presenter that have to wait. We are running a bit late, but I hope it's fine for Kaspar and Iain to wait a bit.
No problem, I can get a coffee as well.
It's very simple.
But let's restart again. So I hope you will have at the end of more time to discuss. And I'm sorry also for Iain and Kaspar, but actually there is Rizwana and she had a problem for the connection. So if for you is fine, she will present now. She has a short contribution of 5 minutes, and after we will move forward with the presenter. I hope it's fine with Iain and Kaspar. I'm sorry. So
Yep, of course, no worries.
okay, please share.
Good afternoon, everyone. Let me share my screen. So is it visible?
Yes. Yep. Please go ahead.
Yeah. So good afternoon, everyone. So I'm Rizwana. I'm working as a research scientist in University of Sussex, UK. So I'm going to present on design and development of a collision-safe robotic manipulator for the nuclear decommissioning. So this is the typical scenario of the nuclear chamber, nuclear cell chamber that is usually used. So here in the nuclear chamber, the radiation level is very high, and there is high risk to the worker's health. And in the high radiation level, there is high chances that the sensors and the hardware will malfunction. In this scenario, the inspection ports are around 150 to 250 meter, and inside the chamber there are usually a lot of network of pipes are there. So here the objective is to measure the radiation level inside the chamber by inserting the robotic manipulator through the inspection port. And these chambers are usually made up of high concrete wall, like with high thickness around a few meters, and the pipes are around a few meters away from the concrete wall. So we need to design a robotic one that can reach the net the pipe, and it can measure the radiation level. So here we are working on the design and development of a collision-safe robotic manipulator, which consists of continuous variable transmission based on actuators at the hinge joint for measuring the contact radiation, and we are going to deploy via the cell wall inspection port. So with this background, I'm just going to explain what is CBT. Professor Romeo has already explained in his talk. He has explained the importance and the working principle of the CBT. So here we are going to use the continuous variable transmission based actuator at the each joint. So this is how the joint mechanism is. So CBT is actuated by a motor, and it is further connected to gears and the pulleys to the joint. So in the CBT, we can change the range of transmission ratio by varying the geometrical configuration, especially here the axis of rotation of the ball element, it changes. That changes the transmission ratio. So the change of the configuration is self-adaptable. So without any sensor feedback, we can easily change the transmission ratio. So that is the beauty of the CBT. So here we are going to implement the CBT mechanism with the robotic manipulator at the hinge. So when the increase in the torque at the output disk, which is going to convert it by the axial force by one coupling here, you can see in the left-hand side diagram, and the traction force between the ball contact surface and the output disk changes, and the ball velocity also changes, and that turns in the displace the toroidal disk. So as the ball displacement alters the configuration, which changes the transmission ratio. So this is how we are going to implement at the joint of the manipulator to do the safe collision. So this work in the preliminary stage. We are still working on the CBT design now. So this is the arm configuration based on the cross section of the inspection port. Usually the inspection port are 200 to 250 mm. So based on that, we have finalized our robotic arm, which is around 170 mm in the diameter. So this is the robot joint configuration. We have around 4 joints here. One prismatic joint, 3 revolute joint, and these are the link configurations, and this is the transmission path that we are going to use for the entire robotic arm. And this is the workspace analysis. By considering the varying the link length, we found that we can able to get around 1.5 to 2 meter of workspace, which is required for our robot manipulator to reach the network of pipes inside the cell wall. So summary, so we have just, since I told you it is the preliminary ongoing work, and with the kinematics and the workspace of the robotic one was analyzed. And based on the joint static torque at the home position, we also finalized the CVT dimension, and also we analyzed the torque produced by each CVT and what is the torque required by each hinge motor. And we finalized the speed of the motor and the transmission ratio for the each element. So here we found that we need we need motor torque of maximum of 9.3 Newton meter at the joint 3, and for other joints, for the joint 1 and 2, it is quite lesser. And we're going to run the motor for the CVT around 50 RPM for joint 3, for other joints 25 to 30 range. So with a reduced transmission ratio, we can get around 2 to 3 RPM at the hinge joint, because we want to measure the radiation level for which the robot arm needs to move at very low speed, which is maximum 2 to 3 RPM is essential for our operation. And depending on the motor and the CVT length, we can integrate a belt drive of maximum transmission ratio 3.2, and the bevel gear drive of maximum transmission ratio of 3 can be integrated. And this work is in progress. Currently, we are working on the solid modeling and the fabrication of the each parts. And yeah, so that's the update of this work. Please let me know if any feedback on my work. Thank you.
Thank you. Thank you very much, please, for your presentation. And do we have any question from the audience, also for the online audience? So I have a question regarding your workspace.
Yes, please.
So is I think slide number 5. So like in this, do you consider all the singularity of your robot?
Sorry?
Did you consider also the singularity when you?
Yes, yeah, we have considered the singularity. So here we are considering the twisting angle is around, all the angles are around -70 to 70 degree. For we have 3 revolute joints for the joint 2, joint 3, joint 4. So for each one we are considering -70 to 70 degree. So so in that range we don't find any singularity here.
Okay, and also like is like did you try different configuration of, like now you have one like 3 revolute joint, 1 prismatic, right?
Yeah, no, we have only one currently, because as I said in the first drawing, yeah. So here we have the constraint in the space, because this first joint has to be in prismatic, because there is no other option, because we are not going to do any inspection here. So this joint has to be prismatic. So that option is gone. So remaining we have 3 joints. So with in order to map a point inside the like 3D space, I think 3 joints will be redundant here. So that's why we are going for only 3 revolute joints in order to get better, like more large workspace.
Okay, so you didn't still consider the reachability of inside this workspace. So like you have this kind of, I don't know, like limitation on the wall and obstacles. So have you considered to do study on the reachability based on this specific like map, or maybe you need a map of this environment?
Yeah, I'll be note on that, and I'll working on that. So here actually I fixed the prismatic joint, this one. Remaining 3, the workspace that you are seeing, that is only for these 3 revolute joints, because finally this is going to work. And if let's say the network of the pipes are further away, so which can be managed from the prismatic joint by translating the arm along this port. So that's why this workspace is only for 3 revolute joints. Yeah, this one.
Okay, thank you. Is there any other question? Okay, then thanks a lot, please, for joining so early. And
yeah, thank you so much. Thank you so much. Sorry about it.
Okay, it's fine. So and now let's move to our next speaker, that is Dr. Iain Darby, and is from the Nuclear Decommissioning Authority.
Hello, so I'm just going to try and share my desktop down number 2, I think. That. And could you just confirm that you're seeing the presentation in full screen mode, please?
Yes, we can see it and we can hear you perfectly. So the floor is
Great.
yours.
So good afternoon, everyone in Japan. Sorry I can't be there. Good morning to anyone who's roughly in my time zone online. Thank you very much to Angela, the organisers, and also Kaspar, who's speaking afterwards, for inviting me to give a talk today based on some of the work at Dunray. Should just emphasise that I personally work for a company called Dunray Site Restoration Limited, which is the company that is responsible for the decommissioning and remediation of the Dunray site, the former site of the UK's fast breeder reactor programme. It's a wholly owned subsidiary of the NDA, and the NDA is the overarching entity responsible for decommissioning in the UK, but I'll go into that into some detail. If just at the beginning, to say if you're wanting to contact me afterwards, you can find me on LinkedIn. I'm also the co-chair of the NDA's Nuclear Waste and Decommissioning Research Forum, which is a lot of activities. So if you're looking to get some more information about what's going on in UK decommissioning and you're struggling to find a contact, please reach out to us and we'll happily direct you to someone that can give you the assistance and writing a case for the particular piece of research you want to do. We have lots of jobs that we need to do. So to move on to the subject of the talk, I was asked to do a talk on the model behaviour of radioactive particles. You might be wondering what that meant. To us, for this talk, we use particles as almost a colloquialism about some radioactive material that's ended up in the environment where it shouldn't be. So both Dunray and Sellafield have a programme monitoring outside the fence line on beaches to look for fragments of irradiated nuclear fuel that have washed back up onto shore after having been discharged. So that when I'm talking about particles, it's small fragments of cladding and material that were accidentally and inadvertently discharged in times gone by during what we now think of as a bit more of a legacy phase, the phase of previous operations, and they now pose a problem in the environment and both to people and the environment, and we have responsibilities both from our regulator but also just to general society to take care of that as a problem. So that's what we're focused on. I don't actually have robotic solutions to this at present, so I'm going to give a couple of examples, and the ask in the kind of room is for engagement from the community on thinking about the systems that are being developed by you and the challenges that you're responding to that might give us some help at solving this particular problem for decommissioning our sites. So with that, I suspect rather a lot of you don't know anything about Dunray or where Dunray is. So I'm going to try and show a short video. It's about 2.5 minutes long, just to give you a kind of orientation feel. Please let me know, someone, if it's not working, if it's sound, if it's too juttery and it's not any good, I'll skip it, but I'll give it a go. So you can see overall our site there, the golf ball is the kind of famous structure. See it? It's on all our logos and our little badges in there. So it's quite a large site right on the coast. That's the sphere for the Dunray fast reactor. See some of our staff working inside. This is some video internally from the Dunray fast reactor, the breeder fuel removal project. It's a large construction site. An awful lot of what we're doing is building new structures as containment and stores. Some work outside in the environment. Radioactivity is not the only things we have to concern ourselves with. You can see some examples there of the beach management. practical work of decommissioning actually looks like. It's guys dressed up in suits. That's our low-level waste vaults, just off the main site. This is a really interesting project that was to go in to melt a sodium heel pool inside the prototype fast reactor, which is one of our major challenges the last couple of years. So that's the Dunray site itself. Hope you kind of got there a feel for the range and the type of activities that are going on a nuclear decommissioning site. A bit of background about the NDA. So this is the organisation that was generated in the Energy Act in the UK in 2004, and they are the entity that are effectively the client organisation for Dunray and the other sites, who hold the responsibility of cleaning up the 17 sites. So you can see in the map that's there, the locations of all the sites. You'll notice that Dunray is furthest north. There are a couple of other sites in Scotland, Hunterston and Chapel Cross. There's the bulk of the radioactivity in the mission is at Sellafield. Nearby to that's the low-level waste repository. We have the Magnox sites, which are going to start to become into decommissioning because they're moving that program forward. So the mission is going to take quite a long time. Getting to this is something like 100+ years and a sizable amount of money to deal with the legacy from the earliest phase of the UK's program in civil, particularly civil nuclear power. So just to continue on about Dunray, actually its orientation. So we're really right at the north coast. It's not so easy to get to us, but it is worth a visit if you can make it up here. And you can see a picture of the site that's relatively recent. You can see how close we are to the coast. If I put a pointer on. So you can see DFR is here. This is the complex for the prototype fast reactor that's down here. This is the third reactor that was on site, is a materials test reactor. The low-level waste vaults are up here. This is the area that we refer to as the fuel cycle area, where effectively the reprocessing took place. Full reprocessing change for the uranium activities. We've got some laboratories, and then a couple of interesting things. So this large concrete structure here is the shaft isolation platform. This building covers the top of the shaft, and this is quite a famous project where there's a core down to a tunnel for the offshore discharge. That was filled, and this is one of the bigger projects that Dunray. Particularly showing you this photo is to start the discussion on particles, where you can see the beaches. So you should be able to see that we have access here through a gate, and you can see this is what we call the West Foreshore. So there's actually an old historic castle here, but this is the West Foreshore beach, and then we refer to this as the East Foreshore beach. You can see that it's not such an easy environment to go out and do survey work, particularly if we're going to send some robots, which is what I'm going to ask you to consider doing later. So this is the two beaches that are really at the Dunray site, the East and West Foreshore beach, and then I'll get into where the other beaches are. Last little bit of word about the history of Dunray. So its purpose was set up to do the fast breeder reaction program. And so they set up a materials test reactor, they set up the DFR reactor, starting in about 1954. They did operations in 57 and 58, went through the 60s. We built the prototype fast reactor. And you can see one picture here, 1983, I'll get to in a minute. We first realized that there was radioactive particles discovered in the beaches. And since that time, there was a activity to look at recovering that material and understand the conceptual model of what was going on. The site shut down its reactors in 1994 and stopped doing fuel processing in 1996. And since then has been in a phase of decommissioning operations. The company Glovnea was created in 2008. Went through a period of what we call the public body organizations, and then it was taken back in-house as full ownership by the NDA in 2021. And as of next year, Glovnea will also join the other company that was called Magnox, look after Magnox reactors, so that there'll be a combined entity. So that's enough for history. So to actually get to particles. So as I said, particles were fragments of irradiated nuclear fuel. And they were first at Glovnea, they were first identified in 1984. And then subsequently in the early 90s, where it was realized that there was a bigger problem than previously been anticipated. This is a piece of work that's got a great deal of interest from stakeholders, as I'm sure you can understand, in government. And our regulator is SEPA, the Scottish Environmental Protection Agency. And the work that was done, particularly in the 90s and early 2000s, was to understand the level of hazard that would be to people in the environment. So the way that we manage particles is that we have three categories in terms of how we go and look for them and detect them and understand them. Particles that are classed as significant. This is where deterministic effects might be possible in a few hours after contact time. Those are particles for which the cesium content is greater than a megabecquerel. In the range of 10 to the 5, 10 to the 6, they're classed as relevant. And then if it's below 10 to the 5 becquerels of cesium, they're classed as minor and unlikely to give rise to radiation exposure of concern due to the way that people would interact with it. So for people used to dealing with radioactivity in sources in the laboratories and check sources like this, you'll understand, these should not be out in the environment. But if you're thinking of it in terms of the detection of this material outside in the environment in wet sand and from very small particles against a background of norm, hopefully that starts to drive your thinking on how you have to use detectors, what size they have to be, what orientation they have to be, and what speed of a robotic system or a remote control system you would need to operate at to have a chance of detecting these. Our requirements are to detect the significant particles down to a depth of about 300 millimeters, 95% of the time, moving at about 1 meter per second, and the wet sand configuration at the Glovnea beaches. Similar parameters will be for Sellafield, but slightly different depending on their local background conditions and the slightly different nature of the radioactivity hazard between Glovnea and Sellafield. So what do they actually look like? I've got a little rogues gallery of particles here. They are about the size of a grain of sand. The picture here is zoomed in to give you a look at. They are small fragments and metallic fragments because they come from swarf, but this zoomed in idea might give you the notion that they're quite physically easy to see. It certainly fooled me at the beginning, but these are really the size of a speck of grain of sand, and you would struggle to tell by eye without having a sensor to tell you that there's radioactivity and then sifting it out and being able to zoom in at it. So that's what these look like, and they shouldn't be there. So around about 1995, we started doing more beach monitoring. You can see a picture of what it looked like it was done. Two guys with what are effectively handheld probes on a stick walking along the beach doing a survey pattern. It's not that much more sophisticated than that right now, as you'll see from, we've got a vehicle, we've got detectors, but we're still largely dealing with single crystal, large volume sodium iodide detectors close to the beach, moving relatively slowly so that we can detect particles. And this is a picture from the nearby beach that's called Sandside Bay, just to the west. I'll show a picture of the locations of the beaches in a moment. As I've said, these particles were a result of inadvertent discharge from operations at the site, which so they go down the outfall and then they've made their way offshore somewhere, and then some of them have come back onto shore. That obviously meant that there was a reservoir of this material offshore. And so in the period in 1997 to 2004, there were diver operations and remote vehicles to go out and try and recover particles from the offshore to prevent them being a cache or a reservoir that could come back onto shore. And that program recovered about 930 particles to reduce the stock of what might be available to come back to shore. We haven't been doing offshore operations since the late 2000s. So the driver for this is always, apart from good practice, as a conscientious operator and dealing with the site, well aware that this material shouldn't be there, but the way that we do it is governed in compliance with the regulators. And for us, the most recent version of the regulations are the environmental authorizations regulations in Scotland, 2018. And this gives us some particular details of how we have to do the monitoring, what the regulator wants us to demonstrate as a minimum to show that we're in control of responding to this problem. So we have stipulations on which beaches we have to monitor, a particular frequency they have to be monitored at, minimum area coverage, the speed that any surveying operations take place at, what our practices are when we recover detected particles, what we should do if we, for any reason, we're unable to discharge a part of these stipulations, and then provide an annual report. Reason I mention this is it's not for academic purposes. So there's good reasons for doing this, but even if you wanted to do it yourself because you weren't being told to do it, in our case, we are given instructions on how we must do it, and then we have to demonstrate that we're doing it in the way that we've been told, or the way that has been agreed, I should also say. So when we're thinking about alternative systems of monitoring in vehicles, it's not in a context without other stakeholders particularly being satisfied that whatever solution we come up with is different to the one that we're using. It has to be satisfied. So changing the equipment and changing the way that we're doing it, and it could be quite different if you're proposing to using robotic systems, then there will be quite a number of tests to satisfy the regulators in particular that the alternative way of doing this is going to be just as good. So the actual beaches that we look at, you can see here a northern survey extract of a map for the local area. You'll see the red semicircle in the centre. That's where Dounreay is located. This is a marine exclusion zone. This is the east and west foreshore beaches, Sandside beaches just to the west. And then we have 2 additional beaches that we monitor periodically throughout the year, 2 times in May and November. And these are what we refer to as the sentinel beaches, to make sure that there's no sign that any of the particles have started to drift further away than the ongoing problem that we're dealing with that we know in this particular area. And the sentinel beaches were particularly important after the period of offshore recovery to see that no material had been disturbed offshore and caused a change in the system. So what does it look like presently? This is again, I'm not sure if this is a photo of either as on Strathy Beach, it might well be. But you can see what we have is a guy in a track vehicle, in a wheel vehicle. It's a little Hellcat, not the Symmetra HX5, one of the newer systems. So off-road all-terrain vehicle. There's a metal box in the front, and inside the metal box are 5 large volume sodium iodide detectors with photomultiplier tubes on them. They're instrumented in such a way that it's 5 independent detectors, and they're constructed in such a way that you get the full width of the coverage of area in front of the vehicle, and the guy in that vehicle drives back and forth on that beach in an overlapping pattern to ensure maximum coverage, looking for an alarm that would indicate the presence of a particle. Sometimes it'll be a false alarm if it's a stone or something like this, but usually when the alarms go off, it's because a particle has been found. I should emphasize no particle has ever been found at Stratton. And no significant particle has ever been found other than at the Dounreay foreshores. So that's the example of what the large area beach monitoring looks like right now. You can't use this system on the East Foreshore beach. It's far too rocky. The access isn't practical. So what is being constructed for use at the moment, you can see is what's affectionately termed a wheelbarrow detector. And what you see underneath here is a single one of these large volume sodium iodide detectors underslung on this wheelbarrow. And then a guy physically manhandles that system over the East Foreshore beach, again, looking for particles that may have come back onto shore. So we'd particularly starting to think about alternatives to doing this. This is quite a physically demanding task for that operator. It's not so easy to get up and down the slope of the beach. And when you get down there, you can see some of the size of the obstacles are quite large. And that system is not the lightest. It's certainly getting up 15 odd kilograms of wheeling around in the barrel, which isn't too much, but if you're doing that for 4 hours or so on the foreshore beach, in the wind and the rain and the wet, it's not such an easy task. So technologies that are being looked at, I've got a couple of examples here from courtesy of a colleague of mine, Richard Hill at Sellafield. There is investigation to using unmanned aerial systems. So they've been performing some tests using a DJI M600, and the detector system that they're looking at using is Sigma 50 detectors, cesium iodide detectors from Chromec. So they've started to do some work in this. They've got a slightly different beach configuration than us to deal with. Some larger areas, but quite flat. Although you can see here that there's lots of rocky environments as well, depending on the status of the tides. So this is a program that's begun. We've got some initial results looking at the lower window. We have a slightly different set of parameters that we're looking at in terms of that they're also interested in our americium signature, which is a difference in the particle radioactivity hazard between Dounreay and Sellafield. So emphasize that is that we're aware of the possibility of unmanned aerial systems at the coast, and particularly up here. It's very windy. It's not the easiest challenge to fly the UAV systems in those conditions. And again, we're interested in finding particles down to about 300 or 400 millimeters in the sand. So at the moment, we're using 5 large volume sodium iodide detectors on a wheeled vehicle where the detector system is as close to the sand as we can make it without the box bumping into the rocks as you go along the beach. So that's obviously quite a different detector configuration scenario than thinking about something underslung on a UAV, which maybe has a payload capacity limit of a few kilograms. But the world is moving on and we're getting there. So this is not us, but this is an exact, you saw it in the little video there on Spot the Dog in the Dounreay Innovation Centre. This is the video that's on YouTube from the University of Bristol, where they successfully deployed Spot the Dog inside the Chernobyl area. And you can imagine using something like one of these kind of systems in an autonomous mode to go over the beach. We will actually start to be thinking about that in an upcoming project. But there are challenges with it, is how we will use the detectors. You saw for some of the size of the rocky objects, how will that be able to go over it? How will it be able to, I'm just going to skip that video because he's talking about
robotic platforms, and also to test our robotic platforms.
Apologies.
The old power plant is a very exciting opportunity for us, an ability for us to demonstrate to your personnel what we can do and how we might be able to help.
Sorry. So to emphasize that point on the difficulty of the actual physical traversal, these are some pictures of these foreshore. In one of the pictures, you can see we're up on the top of the cliff. One of the colleagues, that may even be me, down there on the beachfront. You can see that it's pretty slippy. It's quite a steep slope. There's some large rocks. So it's not the easiest of scenarios to have something like a Spot the Dog or a Ghost Robot or an Anybot be able to carry a detector system. And again, a detector system sufficiently large to be able to detect the particles. But you can see, hopefully, from the wheelbarrow picture and from these pictures that we'd really quite like to find a different way of doing this without sending a guy down there with a wheelbarrow and an underslung sodium iodide detector. There are good reasons for us thinking about how to do this differently, but we have to do it in such a way that we're still meeting the mission where we're finding, recovering this material that shouldn't be there down to the depths where it might be on the beach if it's buried by sand. And one of the things I haven't really mentioned in the talk is just how dynamic an environment this is. You can see here, there's quite a lot of wash. On these beaches, we can have meters of change of sand between the tides. The Pentland Firth is quite notorious or well known in energy circles as being one of the places where tidal might get a lot of tidal energy may be produced, but the Pentland Firth is an extremely dynamic marine environment. So there can be quite a lot of changes in the amount of sand and material that's taken on and off the beach. So last point I want to kind of make is just to kind of give a plug to a successful piece of work that's been done at Dunray, which is inside the plants. But some of the concepts are similar, which is how to get the vehicle down into the location, how to get it through where there's obstacles. And the bit that I haven't mentioned at all here is this is all about detection. But actually recovery is still done by a health physicist who goes down there with effectively a trowel and digs the material out. It'd be nice to have a system that could detect and autonomously recover these particles. And so that final act of sample collection is also something that needs quite a lot of work. So most of the talk there was about things, the challenge that we have and things that we'd like to do with a robotic system we don't yet have. Just to give an example of, there is works in progress. I know Barry's in the audience and I'm sure you can go and talk to him if you want to know more. But there is a very nice successful project in one of our laboratories that was to develop a robot called Lyra that went down into a ventilation system in a central corridor. And you can see they overcome quite a lot of challenges in terms of the loose material that was down there, the obstacles, how do you get it back, how do you detect if there's any hotspots, and how do you collect samples to be able to do further analysis. So although that's an example of inside the fence line, a lot of the thinking that went into doing that autonomy, that robotic system inside the site, some of the similar challenges of the size of detectors, payloads, and how to do things are applicable to doing the same challenge in the outdoor environment, although there are additional challenges to do that as well. So with that, I'm sorry I went on slightly longer than I planned to be able to take some questions, but I think that's all I've got to say for now. Thank you very much.
Thank you very much for your presentation. And do you have any questions from the audience? Okay, I wanted to ask, I mean, it's very challenging. I think at the beginning of in my introduction, I talk about the environment that we have to work on. And I think you showed us very challenging task for our like community. So I'm wondering, you want a robot that can go also under the in the water, or you're just looking on a robot that can easily is a big word, but that can navigate on the score on the beach and grasp the particle? Because you showed two tasks, one in which you are using kind of a one-handed device or like mobile device for the beach, but also I saw a task in which you had a person underwater that was grasping the particle. So
yeah, so for our chat at the moment, we're not doing any further offshore recovery work. It's not deemed necessary right now. Following the successful campaign to recover Akasha particles offshore, the program in the last decade has only been the onshore task. There may be in the future, when there's other decommissioning tasks that require offshore work, there might be some interest in other underwater marine systems. Actually, we have interest in underwater marine systems, but related to things we call ponds rather than specifically to the beaches. In this case, for the outdoor environment, what I'm focused on at the moment is investigating whether a robotic system that can be on the beach is viable. and that's still, I mean, we don't want it to go swimming, but the weather can come in pretty fast. It's a pretty rough environment on equipment and personnel. So it may not have to be able to swim underwater, but it certainly is going to have to be able to stand getting pretty wet.
Hi, so how frequently do you survey any given section of beach?
So the requirement on the beach monitor at the moment is set that we should do, particularly the foreshores, for instance, we will do a survey of those every 2 weeks. And this is the decision that's been taken in terms of everything's done subject to optimization as well. So that we need an estimate and a conceptual model of what the likelihood of change is and the ability to detect the particles. What I would say is that it comes back to the notion of that 2-week timescale, or effectively in Sandside Beach, there's almost some part of the beach is being monitored each day. It's based on the way that we do the detectors and the way that we survey at the moment. So if we had a different set of detectors and a different understanding of the radioactive environment at the beach and our ability to detect particles with a high confidence level, I would suggest that would change how one thought about the frequency of doing the beaches. It might mean that you're out there for shorter periods more frequently, or it might mean a more intense survey less frequently. I think it's driven not just by a TikTok schedule, but it's given by what you think the efficacy of the survey effort is. Last point just to mention is it's logistically it's a wee bit challenging because obviously tide and time wait for no man. So the length of time it takes to do the deployments down there gives you differing windows throughout the course of the year. So throughout the course of the month and then throughout the course of the year on when you can access different parts of the beach. So there are some periods where there might be slightly longer than a couple of weeks between each survey point, for instance, in Sandside Beach, depending on how the tides were and whether you were actually able to drive that tracked vehicle down to that wet part of the beach sufficient, that it's dry enough sufficiently for you to be able to do that survey, or whether you have to wait an extra week in order to be able to access that point in time. So the survey frequency is linked to the ability to do it and linked to, the physical access and linked to the detector systems where you're satisfied that you're out there detecting frequently enough that you're mitigating the risk of harm that is ultimately the primary mission. Does that make sense?
Yes, thank you.
Hiya, sorry if this is a little odd. Have you considered looking at the locomotion solutions that the Mars rovers employ? Because they need to deal with sand and rocks of various sizes. Just wondering if you'd looked into how they drive their wheeled ones around.
So the short answer is no, I haven't. That's a good point. I also don't want to lead you astray in thinking that we doing Ray are a bunch of robotic specialists. We are a group of people that have a challenge and a need and a willingness to work with the expert community, but we need to come and work with you. So it's a good pointed to me, and I've got some. I'll do some research on it, but the details of yourself and your community would also be very familiar with what you're talking about. I don't actually know what was special about locomotion solutions for the Mars rovers, but you've just given me some reading that I should go and do to become more aware. So thanks very much for the question.
Yeah, I can suggest Airbus site in Hertfordshire has like a Mars yard where they test all the rovers, so you can see the videos or you can go and ask them. They might help you.
That's great. Thank you very much.
Thank you very much. I think there was also a question from Kaspar. I don't know.
Yep, if we have time for a quick question. Thanks
Yes.
at first. Thanks to Iain for a very nice talk. You mentioned drones in your presentation, and I'm wondering how feasible is that really? First of all, considering that these sensors look quite heavy. Secondly, you need to probably hover fairly closely to the ground. And you also mentioned the weather conditions. So what are your thoughts on drones? Can that go forward?
So it's something that, so I think there's so the picture I showed was of Sellafield doing it. I think there are different conditions for Sellafield and doing it. And that's why I think they're starting first. It's something that pops up in discussions pretty frequently because this comes out from time to time. It's not a particularly new idea. Occasionally throughout the past, people have contemplated helicopter surveys, or even if it's the kind of Yamaha arm axis. At the end, the reason nothing like that has particularly come to pass before is you end up in the position of the optimization of what is the justification of the cost and effort and the practicalities of doing it. Now, what I would say is I'm not without interest in the current round of looking at using such systems. As I know you know, Kaspar, I've done some work on this myself. I think some of it is linked to more sophisticated data analysis. So in terms of a better understanding of a high fidelity map of the background conditions, and then post-processing and understanding if it's changed rather than the same kind of health physics detection alarm. But for Dounreay, at the moment, at least based on my experience, I still think it would be pretty challenging to use one of these light UAV systems. There are a few days a year where you would be able to have a confidence level in using it. Having said that, over the course of the last decade, the systems are getting much better at flying by themselves. When I first started doing it, it was quite difficult with fighting against the wind, and to hold the GPS hold was particularly poor. So it was always, you'd end up burning a whole battery just trying to do a position hold of a few meters. This has very evidently got significantly better. So as the systems improve, particularly the control and analysis, I will have to at least revisit the question of can the pilot, the autonomous flying part of it really assist the pilot in being able to hover very close to the ground without really pilot intervention. At that point, things might change, but I think for now I can see a way of us using it on Sandside Beach in reasonable weather conditions for part of the year. But for a good part of the year, I think, there are times of the year where we can't physically go out on the West Foreshore because of the wind and the rain. And that's with all other safety systems. So it's not, I don't think we'll be using UAVs, especially in the West or East Foreshore, anytime soon. And at the moment, my principal interest is on a robotic system for particularly the East Foreshore, to allow me to get the human operator off the beach and not using those wheelbarrows anymore. That's what my particular motivation is.
Okay, thank you very much. Okay, you can quickly. Okay.
I just wanted to ask, is there a mandate for how long you are going to continue these surveys, or is it just indefinite?
So I'll give you an unsatisfactory answer. The unsatisfactory answer is we will continue to monitor it until such time as that the risk to health is mitigated, and that stakeholders are convinced that there's no further need for monitoring. So the reason it's an unsatisfactory answer, I can't tell you that the monitoring will discontinue 3 years, 5 years, 10 years, 15 years from now. You can build a picture in your own mind of when the need for it will end. The predominant hazard comes from cesium. We have an idea of when they were discharged, radioactive half-life, and the fragmentation of the material fragmentation of the particles in the environment to take big particles that would be classed as the significant particles with a major health risk and making them into smaller components. So there are radioactive decay and mechanical processes taking place that will set the limit of how long we have to continue to do this. But we don't have as thorough an understanding of that process as you would like to have to be able to say, we will stop the monitoring on a specific date. Does that make sense?
Yes, thank you.
Okay, thank you very much. Thank you very much for your talk. And I hope some people will contact you with some solution for the very challenging problem that you proposed to us. And now is the time of our next speaker, that is Professor Kaspar Althoefer. He is the head of the Center for Advanced Robotics at Queen Mary University. And it's very nice to see you, Kaspar.
Yep, hi. I think you can see my screen already.
Yes.
And you can hear me, that's good.
Yes.
So yeah, first of all, thanks to you in particular, Angela, for inviting me to present here today. Unfortunately, I cannot be there in person. But yeah, I hope I can give you an overview of the work that we have done in respect to immersion robots and growing robots, in particular for the nuclear environment. And so I have looked at pipe navigation, inspection, and the delivery of sensors to characterize these environments, to find out where nuclear radiation is coming from. So this work was very much part of NCNR, or the National Center for Nuclear Robotics, which was a very recent project funded by the main research council in the UK. We call it now UKRI, United Kingdom Research and Innovation. And previously we called it EPSRC, Engineering Physical Sciences Research Council. And so that is really what I'm kind of focusing here today. And at Queen Mary, I'm the director of the Center for Advanced Robotics at Queen Mary, as we call it. Thanks also for organizing my talk in that way. So Iain had the chance to speak before me, and I think that fits very well, because that work that I'm presenting now will actually continue in collaboration with him. Yeah, and so let me now go to the next step. So to give an overview, I don't know, can you see this bar here at the top? Can I remove that? Maybe I move that to the side. Oh, that's maybe better. Good. So number of activities that have been happening at Queen Mary within that project NCNR. And so we have developed these growing robots particularly for sensor delivery. And I will talk much more about that in a minute. But we have been also developing a range of tactile sensors, for example, to do surface property examination to find cracks in surfaces, in concrete surfaces, for example. We have been also working quite a bit in grasping and manipulation, for example, learning from humans on how to improve manipulation, in-hand manipulation, but we have also been looking at inflatable grippers, and I will talk about that also very shortly later. Teleoperation and the navigation of robots in remote environments was also an important element of that work there. And this work we have summarized in an article, so whoever is interested to get an overview of that work, we have the suite of robotic solutions for nuclear waste decommissioning, an article from last year. So today in my presentation, I want to focus on eversion robots that can move through pipelines, and also explain what eversion robots are, and then also to look at the navigation capabilities of those, and how we can control the pose and position of these kind of robots. I will also touch on sensors that we have developed that can be integrated with these robotic devices to tell us more on where they are and how they are moving about. And yeah, as I said, very shortly, I will have a look at those soft inflatable grippers that we have been also developing. So first of all, looking at these soft growing robots that we can use in these very unstructured environments, in particular to deliver sensors into these areas. So yeah, there's a need for these kind of robots for sensor delivery. We have as we have heard today many times, environments that are highly irradiated, and sensors and other tools need to be now brought into these locations. So, for example, the inspection of contaminated pipework is important. We might want to move through very small openings into areas that are very highly radiated by nuclear radiation. And other areas could be large cells, tall cells, where we need to access, when we need to have access, and when we need to get a better understanding on the situation in there. Obviously, at all times, there is a difficulty that these areas can be very highly irradiated, and so we need to have sensors, robotic structures that can handle this kind of radiation. So we have been looking at immersion robots, and so I use that slide now to explain what I mean by that. So these are the kind of growing robots that we have been developing for some time. I would like you to also look at work by Hawks and Okamura, who have been also working in that area. And you might have seen some nice videos about the Vine robot. So our work is very similar in that respect. So these are now robotic structures that don't look really like the kind of robots that you might be used to. So they're made of fabric material or thin plastic sheets, and they can be inflated by air. And one of the most important points is that they extend from the tip. So a bit like a plant that is growing from the tip. So we take the inspiration from there, although our mechanisms are quite different. In our case, we have a sleeve that is folded outside in, and then through air pressure, we fold it inside out. And you can see that on the right-hand side, how it is moving upwards. I want to make an important point here as well, and might come back to that later again. The movement, the forward movement, is virtually frictionless. There's only slight movement at the tip, but as you can already appreciate from the video that is running on the right-hand side, once we have unfolded a bit, it just stays there. So there's no more movement. And I think that is also very useful if you go into a nuclear environment where you don't want to really disturb, the ground. You don't want to disturb the radiation in those particles there. So obviously now we have this interesting kind of structure, but it's not sufficient to just move forward. So we have been working on creating ways to make them bend and navigate in that environment. And I will run that again, that video. It's coming here. So here on the left-hand side, we are looking at an approach where pouches are just attached on the outside, while on the right-hand side, we have developed a new approach where we integrate now inflatable pouches inside the robotic structure. And then you can see we can achieve a very impressive way of bending that structure. While on the left-hand side, we achieve only very little bending. So we have this fabric-based inflated structure. We have now pouches integrated, which can be, by themselves be inflated. They contract on inflation and then achieve that kind of bending. And we can also do that while everting. So you can see this robot now here everting at the tip and at the same time achieving the bending motion as required. So for example, to move around obstacles into an environment. And we have applied this in different areas. So we have been also collaborating with a London-based company called QBot, who are interested in developing robots that can inspect the voids under buildings. And so here you can see one of these eversion robots now moving along, and I speed up the video a bit. And as you can see, it bends around the corners and can move further down into this void. Here are a few more examples. So again, you can see these robots extending from the tip and then when required, achieve their turns. Pipe inspection, also an important element in this context. And here I have to say, it's actually a very straightforward process. What you're going to see is at first moving through a small opening into a larger space behind that opening. So yeah, very narrow opening. And I speed up a bit. And what we have also recognized very well here is that the outer diameter of the inflated structure can be easily larger than the diameter of the opening. And it can very nicely move through that opening and then expand to its full size and continue its journey in that space behind. Now moving into pipelines, again, the eversion robot can handle pipes that are smaller in diameter than its actual structure, the actual diameter of the robot itself. I'm just going back again, run this again. And we can also go through very cluttered environments. And so if there are narrowing areas in the pipe, we can easily circumvent that, move around that. So of course, the integration of sensors is very important. Here is an example where we have integrated a camera, but other sensors like radiation sensors could be easily employed. And as you can see, the camera is now coming out at the end. We can now use our pouches to navigate this robot into different directions and explore a certain area. The disadvantage of the camera is that it is only active once the robot has completely everted and the camera is coming out. However, if you have a radiation sensor that can penetrate or can measure signals through the skin of our robot, then we could also measure radiation information while the robot is expanding. So just a quick detour here. We have done also work on navigation algorithms for point-like robots. So for example, UAVs, unmanned aerial vehicles. So we have this new algorithm developed that allows us to move a drone from a start point to an end point around obstacles, and it outperforms many other local navigation methods and is successful in most cases to reach the goal. It's a magnetic field inspired navigation algorithm, and real great advantage is that there's very little prior knowledge needed to make that work. So the sensor only needs local knowledge. So the system, the algorithm needs only sensors that can acquire local knowledge where obstacles are. Does not need to have a prior information about anything about the environment, and it will work. And it's very fast, I should say as well. So we have applied that also for soft manipulators. So that links more to the eversion robot work we are doing. So you can see on the left-hand side, our algorithm reaching the goal while using a standard potential field method would reach a local minimum at a point very close to the start, because there's an obstacle in the way, and the robot will not be able to reach the goal. While our algorithm, using this magnetic field approach, effectively gets lines of movements around the obstacles along the magnetic gradient towards the goal. And we have applied this to a small soft robot, and you see an obstacle indicated here on top, and the goal is on the left-hand side. And as you can see, also in this three-dimensional problem, the robot is capable of moving from start to goal. Beyond that, we have also looked into modeling our system, our eversion robots. So you can see here the eversion robot in the lab environment, and you can see it from above. And we have used imaging systems to acquire information about the the position or the pose of our robot, and then have used a number of techniques to control the movement of that robot in its environment. And so, for example, we have managed to make the robot now move along a line, and we could show that we were able to do that in a quite repeatable way. So as you can see, we are fairly close to the original line, not perfect, but we have to also keep in mind that this is now a completely soft, inflated structure, and is actuated pneumatically. So very non-linear, very difficult to model, and I think already very good results. We have also looked into controlling the pose of the robot in the case that there are actually external forces, because that is a big difference now when we look at soft robots. They are very much affected by external forces, very different from standard rigid component robots. So as you can see, with different pressures, lower pressures, we are not capable to reach the final position, but then we can change the pressure as part of our control strategy. And then if you apply a very high pressure, then you're capable of moving the payload and reach the goal position as desired and as required. Good. A few words about sensorizing these soft robots. It's very difficult now to implement sensors that are traditionally used in the rigid component robots, because we have soft robots and we want to keep them soft. If you now attach a rigid sensor to that sensor made from rigid materials, you disturb, you know, a main feature of this robot, i.e. being soft. So we have looked into light guides that can be integrated with soft structures. Here we're looking at integrating these light guides with a silicon rubber structure. So you can see that here, you can even see the light inside the structure. And now we have abraded optic fibers integrated here. And the more the structure is bending, the more light is lost. You know? So we are feeding light from one side, receiving light from the other side, and the amount of bending now influences the amount of light that is reflected back again. And we have integrated that into into this kind of soft structure here. And as you can see, as the robot is bending in steps, we can also see that information reflected in the graph on the right, and that is the signal we receive from our fiber, from our light guide. Similar sensors we have integrated now also with a structure that is made from fabric, an inflatable structure. And as you can see, we can now use those fibers, these light guides, to measure the angular position of this type of robot arm. And more work will be done in this direction to get a better understanding of a pose, of the position and orientation of the robot in their environments. Just very quickly also, I want to come to inflatable grippers. So these are very much akin to the type of immersion robots I've spoken about. They're also made of fabric material and could be candidates for tools attached to our immersion robots to move into environments, and so not only to deliver sensors there, but also to deliver tools, gripping devices in these environments. And here again a short video to show how that works. So as you can see, we bring the grasper in the right position, and then if there is an object to be handled, we can pressurize our graspers, and the object can be picked up. And what we observed is that without too much control, we get a very secure grasp, and we can also handle a wide range of different objects to be picked up. There's always the question about, soft fingers, how much force can they actually apply? And if we look at our fabric-based robot graspers, then that is actually quite a bit. So we have carried out this experiment, and the final force that this finger can hold is 10 kilograms, or equivalent to 10 kilograms. So yeah, I think quite impressive for a small finger like that. And I think it also shows how useful these can be in this context. Good. Yeah, I would like to come to the end with my presentation and thank the major funders, EPSRC, our Engineering and Physical Sciences Research Council. They have funded this National Center for Nuclear Robotics, which was actually led by the University of Birmingham. I also would like to thank the National Nuclear Lab, the Nuclear Decommissioning Authority, and Dunray Site Restoration Limited. So you have already heard the talk by Iain earlier, and so the work that I've presented here will continue now through that funding from these bodies. Lots of collaborators. Without those, of course, that work would not have been possible. Before I completely conclude, please allow me to also speak about another conference which is happening next year. ICRA 2023 is coming to London, and please, looking forward to seeing you there. Thank you very much.
Thank you very much, Kaspar, for the interesting talk. And do we have any question from the audience, please?
Hello, Kaspar. This is Romeo Glovnea from University of Sussex. Thank you for your presentation, and I apologize for asking a very trivial question after such a great presentation. But when you inflate those pouches, how do you fold them back?
Oh, okay, good. So I don't know whether you're referring to the pouches that we use for navigation or to the whole robotic device. So the version robot is, that is a very good question. It's not a trivial question, it's actually a very good question. So these robotic structures are very good in growing. They're not so good in when we want to retract them. So what we do is we usually deflate them and pull them back again. That is the solution that we are currently using. And then there is a process to actually fold them outside in again by hand.
How long it takes?
Say again?
How long it takes to fold them back?
Maybe 5 minutes.
Okay.
In this region. I would like to add, I mean, even though I have said that, what I've said applies only to robots who go into the open field. If one of these robots goes into a pipe, it is nicely confined by the pipe, and retraction is actually very easy. So we can very easily, with a tendon, pull from the tip backwards, back to the base again of the pipe. So okay. In pipes, no problem. Outside pipes, still a research topic.
Okay, thank you. Well, if you allow me a comment, because I'm a tribologist, you said that basically there is no friction. I dare to contradict you. Anytime you have surfaces moving against each other, you always have friction. You can neglect it if it's very small, but friction is always there. Thank you.
Yep. Yep, obviously. But when this robot is, maybe I just quickly go back to an earlier slide. Just give me a second. maybe this one here. So in this video, you can see the robot everting. And yes, there is something happening at the tip. But if you look at this part here, it's not moving. It's static. It has moved. And so there is actually no friction because it's like we are laying it down. And once it's laid down, it doesn't move anymore. So there is no friction now between the surface of this robot here and the ground. There's a little bit of friction there. Where I agree is when we start now moving left and right. So if we look at this video here, for example, so no friction going forward, but the moment we start bending the structure, especially once it has been already everted, then of course you have the friction if we pull the robot left and right across surfaces. Thank you.
So thank you for your presentation. I was just interested, I know Festo had some similar arms, but different. Just wondering if there was any crossover between the work that they did with their flexible arms and yours.
Yeah, so I know the Festo work, and these is brilliant stuff they're doing. I mean, I'm always super impressed. However, they don't have this kind of growing capability. So their robot arm is, it is the length it is. While our robot arm, and you can see it in that video, is actually growing from the tip, and so effectively, translating forward into space, and that cannot be achieved with most other arms. I mean, there is work by Alison Okamura and Elliot Hawks, of course, and Satoshi Tadogoro has also worked in that area. And maybe I'm missing one or two others, but that is the fundamental difference. Now, these devices grow from the tip, and other devices, they are structures possibly inflated or possibly made from soft materials and then actuated pneumatically or by tendons, but they cannot move forward from the tip.
Thank you.
Thanks. Excellent talk. So we work with pneumatics as well and the reconfigurable robotics lab, and we struggle a lot with leakage. And I'm wondering, with the extension of this robot, when it reaches really long distances, how do you accommodate for leakage?
Yep. Yep, good question, and I totally agree. It's a very, it's a problem. It's a challenge. So we use an approach where we sew these systems together. Maybe I can show that here in that video. So this structure is made from fabric and sewn along the whole length, and then pouches are integrated. They're also sewn into the structure. You can see the pouches here, and so we use two different techniques. One is to apply latex onto the seams to seal it, and more recently we are using vinyl. So a vinyl layer is applied and then is effectively is heated. So we thermally bond the places that need to be bonded, and in this way we achieve quite a good airtight structure. another approach that we are looking into is also when we create structures from plastic sheets to just thermally, weld them, bond them together. It works fairly well.
Thank you very much.
Okay, we can get the last question from the audience. I'm sorry, we don't do so much time.
Thank you. So I would like to know if this robot could move or just limit by its length. Thanks.
So the robots that we are building are limited by their length. Yeah. So the maximum we have done, I think it was 24 meters so far. They are attached to the base. So it's a robot fixed at the base, and once you have completely averted it, you cannot grow further. Yeah.
Thank you.
Yeah.
Okay. Oh, I see that Iain. So last question. Okay, there is another question. Okay, please go ahead.
It's probably just a yes, no question.
Okay.
Yeah, so thanks. I personally find version robots really fascinating. I was wondering if regarding to like end effectors and sensors, if you guys have thought of like a clever way of having them moving as the robot grows, or do they need to be fixed in space at a certain length?
Yeah, that is a very good question. And yeah, I mean, the video is still running. How can you attach something to an endpoint that is continuously growing? So there are a number of techniques. So we are looking into attaching a cap at the tip, and that can allows then to attach sensors to that. And that cap will effectively sit on top of the tip and be pushed forward by the structure.
Okay. Okay. Cool. Thanks.
Okay. Last question, Iain.
But it's definitely definitely a challenge. Thanks. Yeah.
Please, Iain, go ahead.
I'll be quick. So thanks very much, Kaspar, and I'm looking forward to doing lots of this. I just for the general audience, I think just to understand how much of this challenge we have to do, the amount of pipe work, ventilation, ducting on the legacy sites is immense. Huge parts of our facilities, people from oil and gas would simply recognize as processing plants. There is a phenomenal amount of pipe work conducted on all these legacy things, and the difference between the as-built drawings and what we actually find in the ground, you're dealing with the what's down the back of the couch scenario, just I get thousands and thousands of times. So if I can just encourage lots of people to apply your vast brain power to these kind of problems, the industry really needs it. Thank you very much. It was a great talk, Kaspar.
Looking forward to working with you, Iain, and hopefully we can at least check some pipes out.
Okay, thank you very much. Thank you, Kaspar. It was a very nice talk, and yeah, we look forward to meeting you in London. And yeah, thank you.
Thank you.
And now it's the time of our last speaker, that is Professor Hajime Asama from the Service Robotics Laboratory at the University of Tokyo. Kaspar, maybe you can. Okay, you're still sharing.
Yep, I'm trying to unshare now. Oh yeah, sorry, it's coming. Yep, unshared.
Okay, you can also switch on your camera so people online can see it.
Okay, can you hear me for the online audiences? I hope you can hear it. Okay, so hello, I'm Hajime Asama of the University of Tokyo. So I should be the last speaker in this workshop, but I think the schedule is very delayed. So I try to, make my presentation compact. So actually, today I'd like to explain what's going on in Fukushima, because I'm so much involved in the activities to introduce robot technology to the sites. And also I'd like to introduce the systems we are developing for such kind of decommissioning of the nuclear power stations. And so maybe I think I can skip it. So as you may know, this we have very big earthquake in 2011 on March 11th, and it was called Great Eastern Japan Earthquake. The magnitude was.
I'm sorry. If you switch on your camera, also on the Zoom, people can see it.
I switched on.
Oh, it's on.
Yeah.
Okay, sorry.
I hope.
Okay, it's fine. Please move.
Yeah. Okay. Yeah. Okay. Okay. And then the biggest problem was the tsunami, which happened 30 or 60 minutes after the earthquake, and it attacked this East Coast area and destroyed this area. And more than 15,000 people are killed by this tsunami. And but the another biggest issue was the accident of Fukushima Daiichi nuclear power station, which is located very close to the seismic center. And this is a scenario how it happened. And after the earthquake, the power supply was lost, but the emergency generator was activated and scrum was successfully done. So it stopped the reactors. But after that, the tsunami attacked this nuclear power station, and then all the fuel tanks and the generators were damaged, and the station blackout happened 1 hour after the earthquake. And then the cooling system of reactors and the fuel storage pool became in failure, and cooling water was lost. And then finally, the meltdown of nuclear fuels happened. And due to this meltdown, hydrogen was generated, and the hydrogen explosion happened in 3 units. That's the story. So this is a photo which was taken from the air just after the accident. In this nuclear power station, there are 6 units, and the unit 1, 2, 3 were under operation, and unit 4, 5, 6 were under maintenance. Hydrogen explosion happened in 3 units, 1, 3, 4. Because in the case of unit 4, it was not under operation, but the hydrogen generated in the unit 3 were flux to the unit 4, and this explosion happened. And in the case of unit 2, by the explosion of unit 1, one panel dropped, and it is a kind of a window which can release the hydrogen generated in the unit 2. So in the case of unit 2, hydrogen explosion did not happen. But still, in the case of unit 1 and 2 and 3, they are under operation. So all the fuel in the nuclear power station were melted down. Okay, this is the current situation of 4 units. So already more than 11.5 years have already passed after the accident, and the decommissions were underway. And in the case of unit 2, there is no fuels in the reactors, but they have the very large number of spent fuels in the pools, but they succeeded in retrieve all the fuels from unit 4.
And in the case of Unit 1, 3, 4, all the fuels which were originally stored in the nuclear reactors melt down and dropped to the bottom of the PWR, and even penetrated the bottom of the PWR and dropped to the bottom of PWR. And what we should do is to retrieve all the fuel debris in the Unit 1, 3, 2, and 3, and also retrieve all the spent fuel which were stored in the spent fuel pool. But in the case of Unit 3, they succeeded also in taking all the fuels from the spent fuel pool. So but still there are spent fuel pool in the spent fuel in the spent fuel pool of Unit 1 and 2. Okay. So this is a video which I got it from Professor Okamoto, and it is very good movie to explain how this accident happened. So this is the Fukushima Daiichi Nuclear Power Station. So this is the Unit 1, and this is the photo which was taken just after the accident. And after that, they make a kind of cover to contain the contaminated materials. But now they disassemble all this kind of coverage and making a more stable coverage. And this is Unit 1. So radiation level is high, and this is scenery from the top. And you can see the operation floor. It is has a top floor of this new reactor buildings, but totally damaged by the hydrogen explosions. And this is Unit 2. So the reactor buildings are rather healthy, but they should make a kind of structure to retrieve the nuclear fuels. So this is some kind of structures they are making now. And this is Unit 3. The radiation level around Unit 3 is very high, very high. And they have cleaned all the rubbles on this buildings, especially on the operation floor. And now they succeeded in making this new structure to retrieve the fuels from the spent fuel pool, and they finished the missions. But still, they are working on retrieving the fuels, the fuel debris from the PCV of Unit 3. And this is the way how they retrieve the spent fuel pools. And by the hydrogen explosion, there are lots of obstacles accumulated on the storage. So they are carefully operate this kind of manipulators to pick up all the spent fuels, and it was succeeded. And this is Unit 4, and all the missions were already done. So it means that all the spent fuel stored in the spent fuel pool were already retrieved. And they made also this kind of new structures on the Unit 4. Okay, this is a situation. And okay, and this is a roadmap which was released by TEPCO and the METI, Ministry of Economy, Trade and Industry of the Japanese government. And the decommissioning phase is divided into 3 Phase 1 is this is just within 2 years. This is a period to start of fuel removal from the spent fuel pool, and this was finished. And then phase 2 is period to start to the start of fuel debris removal. It was set as within 10 years, so this should be 2021, so last year. But we could not start the fuel debris removal yet. So it is now planned next year, so it is a little bit delayed. And phase 3 is a period to the end of decommissioning. So it is considered that it will take 30 or 40 years for the decommissioning. So maybe this should be 2051. Yeah, something like that. So maybe I cannot survive until the end. So but please live long and see what will happen in future. But anyway, it is requested for us to develop various types of robotic devices and systems to proceed this kind of decommissioning. So then these are the needs tasks for remote technologies. So they call remote technology instead of robot technology, because they operate the devices from the remote site. Water injection, removal and transportation of rubbles, fuels, and contaminated water, and so on. And investigation, measurement, and mapping, taking images, measuring radiation, and sampling of contaminated dust or contaminated water or concrete core or fuel debris. Maybe we should take samples quite soon. And the decontamination and shielding, fixing of contaminated water leakages, handling, transportation, removal, setup of devices, instruments, equipment, and so on. Waste and contaminated water management, dismantling of facilities. So it's quite diverse. So maybe we should develop various types of robot technologies. We need to develop some kind of portfolio of the robot technologies to to respond to this kind of needs. And this is another video, which explains how this accident happened. So by losing the function of cooling down the reactors, so all the fuels were melted down and dropped to the bottom of the PCV, RPV, and then after PCV. But this kind of meltdown fuels, some of the fuels went over this area, and this area is called the pedestal. This area is called the pedestal, which is structures to support the RPV reactors. But it is very difficult to access this area. That is one of the challenge we should tackle. And because it is covered by very thick wall and very limited measures to access this area. Okay, and so far there are several types of robot systems developed by IRID and some kind of plant manufacturers. And for unit 1, they developed this kind of the morphological robot systems to investigate this area. This area is a kind of inside of PCB, but outside of pedestal area. And it was very successful. This robot is a kind of snake-like robot when it was inserted to the PCB, because the opening is very small, and they use a kind of pipe, which is called penetrations. And but after insertion, the shape of the robot is transformed to this kind of shape, and it can, as a move on the grating floor. And this is a robot. This is a very small ROV which can operate underwater environment, and it was also inserted from a kind of penetrations, and it could have say access to this pedestal area and got sent us a very interesting images and movies. And this is another type of robot which was inserted to the Unit 2 pedestal areas. It was not so successful because there were obstacles which were unpredicted obstacles, and but after that they developed this kind of hanging camera devices, extension rod, and it is a kind of telescopic type cameras, and it was very successful, and they sent us a very clear image. This is a transformer robot, and how they operate this robot. Maybe I should skip it. And this is the ROV, which were introduced to the Unit 3. Okay, and so currently they are developing a very long arm for trial retrieval of the field debris from Unit 2. So this is the image which were observed by the camera device I introduced in the previous slides, and the image is very clear, and it's very interesting. So there are lots of melt or structures or sediment and rubbles, and some of them are stone-like objects, so you can pick up. And some of them can be considered as a kind of field debris, but some may not be the one. But anyway, they are trying to retrieve some samples of this kind of objects in these areas, and analyze the what is it. Okay, and so the arms they are developing is very long arm, and so that should be I'm sorry. Okay, so this is a kind of arm, and it is originally developed in UK, Oxford Technologies. They use a kind of technologies which is for the jet reactors, and but they make a very big one comparing to the jet arm. And they are still making a test in a mock-up facility in Naraha in Fukushima. And it is very difficult to control this kind of very long arm, because it's a kind of cantilever type arm, so there is some kind of vibrations. And also, it is very difficult to navigate this robot arm to insert it to the pedestal area with avoiding many obstacles. And okay. So, okay, this is another story. Yeah, this is the story how this robot arm can be inserted to the PCV, and also to try to investigate the pedestal areas. So this robot arm is folded originally, but it is inserted by stretching it out. And some part of the platforms in the pedestrian areas are broken, and there is a kind of hole. And so they try to insert this kind of arm from this kind of hole and access this area. This is a kind of test, operations. And it is not, it is very challenging mission. So I hope it would be successful. And another one is the investigation of PCB of Unit 1. So these are the very recent missions, and several types of ROV were developed by IRID. And it was some of them were already inserted to this kind of torus room. This is a kind of underground structures, but in the case of Unit 1, the field debris is not stored only these areas, but it should went beyond these areas through the some kind of windows. And they observed already some of the field debris in this area also. So the mission was very successful. They developed several types of RAV. This is one of them. And this is a kind of ROV-A. They developed ROV-A2 or B or 3 or so they make a kind of several missions to each ROV and trying to use it in sequence. And it is very exciting to see the movies this robot have already obtained. And even in this kind of areas, you can observe some kind of melt or dropped structures. And some of the structures were already deteriorated. And so what they are doing now is to make a kind of plan to introduce another type of ROV to go into the pedestrian areas and observe what's going on in this area. Okay, and this is the situation. So, but actually, as far as I know, so they developed many kinds of robot systems, and I think more than 50 kinds of robot systems were already introduced and used for decommissioning of this Fukushima Daiichi nuclear power stations. But they need still more. And most of the missions are successful because they made a kind of test in the facilities, and they made also training of operators. But we have some kind of, unsuccessful stories. So we learned some kind of lessons from such kind of unsuccessful stories. And some robots were stuck in the areas and unrecoverable. So we should analyze what are the factors of failures. And this is my considerations. So there are direct factors and indirect factors. For the direct factors, we have some kind of communication failures or misoperation or malfunction by radiation and so on. And for other factors, one of the factor is prototype. So some of the robot systems are not product. So it is just developed for some kind of very specific missions. So it is not so reliable. So that would be the reasons why it is not successful. And another very big challenge is we should design the robot system even in the situations we don't know the environment exactly. So we should assume many kind of environmental situations, and we should design the robot systems. And these are the measures of direct factors. And maybe I have not so much time to explain in detail, but the interface is quite important because most of the robot systems is teleoperated. And some of the, how say, failures, how say, happened because of the, how say, lack of the situation awareness. So we are trying to improve the human interface, to develop a new human interface to improve the situation awareness. That is bird eye view systems. So now we have Komatsu-san, and he's assistant professor of my laboratory, but he developed the new such kind of the bird eye view system in which you can change the view angles. So it's an arbitrary view system. And it will facilitate the teleoperations. And this is also very important. And we are also working on very basic research. It is more psychological research to analyze why we say, make miss operations. And so from the psychological aspect, we have some function, a brain function, which is called the sense of agency. And if we have more than 300 milliseconds, we may lose the sense of agency. So that is the reason why it is very difficult to teleoperate the robot system which have in which the there are more than 300 millisecond time delay. Okay, then maybe I'd like to skip it because I have not so much time. But it is very interesting to see that if we have very good human interface, and the human interface and the human operator can share some kind of objective which should be achieved, we may say the increase the sense of agency of operators, even if we have some time delays. I'm sorry, I skip it. And testing is also very important. So JAEA constructed new such kind of facilities to test many kinds of robot systems. And it is now used for the long robot arms for trial retrieval of the field debris. And also they developed very big facilities to test the robot. That is Fukushima Robot Test Field. You can test aerial vehicles or ground vehicles or underwater vehicles in these areas. And many companies and research institutes are using these facilities to when they develop the field robots. And I think I have not so much time, but so briefly, I'd like to introduce what we are doing. So we carried out a mixed program, which is called Human Resource Development for Fukushima Daiichi Decommissioning based on robotics and nuclide analysis. And the main objective is human resource development, but we are making a kind of research by involving some PhD students or young researchers, postdocs, and so on. And so we focused on the on-site or off-site analysis system. So this is on-site analysis part, and this is offline analysis part. On-site analysis is a kind of robot inspections, and also nuclide analysis, gamma ray CT, and offline off-site analysis is a kind of sampling of field debris, and then nuclide analysis. It's a kind of microanalysis. And so in this project, one of the students make a kind of made systems to localize the radiations by using robot motions. And the basic idea is CT, CT scan-like approach. So we introduce a kind of mobile robot systems in which the radiation detectors and the laser rangefinder is installed. And by motion of the robot systems, we can get the sensory data, multiple sensory data from multiple locations. And we use the Compton cameras to get the radiation informations. And from this Compton camera, we can get some kind of information and which directions Compton camera can detect the direction of radiation sources of by combining multiple Compton cones. And also we use some kind of SLAM techniques. We can localize the robots, robot locations. So we integrate this kind of information and finally get the information on radiation source locations. And we are also developing such kind of robot motion generation systems to localize with localizing radiation sources. So it's very simple. We use a principal component analysis, and if radiation measurement is very weak, the robot try to approach to the radiation source. But it is has a more than certain level of measurement, then robot tries to rotate and to localize the radiation source. So then we can generate some kind of autonomous motion like this, and with localizing a radiation source. So it's a quite simple method, but it is very successful. And then we are now doing another, the next project, which is called Human Resource Development Related Remote Control Technology for monitoring inside RPV pedestal during retrieval of field debris. The idea is to deploy some kind of rail system in the pedestal areas and introduce the mobile robot systems on which can move on the rail. So this is a kind of two-step procedures to introduce the robot. But this pedestal area should be monitored very long time. So we believe that this concept is very effective. And we are now developing such kind of, devices already. And this is structures, so which is introduced from the penetrations. And it is deployed on the pedestal areas. And then we introduce this kind of mobile system on this platform. And Fukushima, Professor Takahashi from Fukushima University is also developing this kind of very simple manipulators, but I have not so much time to introduce it. So this is very interesting that this robot have some kind of low melting point alloy in each joint. So we heat the joint and make it free, and then cool it down to fix the joint as the arbitrary orientations. So by repeating this kind of procedures, we can make a kind of structure of manipulators. And we are developing this kind of also teleoperation systems, and Professor Yoko Koji is developing this kind of a human interface with multiple displays. So if we use multiple displays, the programs of the operator is each camera has a different coordinate systems. And there are two consistencies. One is reference frame consistency, and another one is posture consistency. So they are discussing how to accommodate this kind of consistency, and also they considered two mode, position mode and rate mode, and which kind of has a calibration would be most suitable for the human operators to operate the robot system easily. Okay, and some Professor Takahashi and Shimazoe is working on radiation monitoring devices, very small neutron and gamma detectors. And Dr. Kawabata and Hanari in JEA is working on the 3D reconstruction of the environment. Okay, I'm very sorry that I have no time. And currently we are also working on UAE Japan collaboration project. It is novel mechanism, novel mechanism. I cannot read it. For efficient field retrieval. But I think Romeo or Angela introduced already, so I'm sorry, I'd like to skip it. So technological challenge. So most of the systems are remotely operable RT systems. So distributed system human interface communication is very, very important. But we should improve the situation awareness, and also autonomy and body consciousness is also important. Okay, I skip it, and then I'd like to summarize my talk. So technology challenge is adaptive autonomy, I think, and it is also very important to understand the human. And not only for the research, it is very important to make it usable in the sites. So societal dissemination is very important. And finally, I'd like to emphasize that international cooperation towards human well-being and sustainable, peaceful global society. So we need to concentrate the wisdom of the world for the decommissioning of nuclear power stations, and solidarity we call harmony. That is very important. Thank you very much for your attention. Just one announcement. So next year we have IFAC World Congress in Yokohama. So currently I'm the president of IFAC. So please join. Okay, I'm very happy to accept any questions if you have.
Please.
Apologies if I've already mentioned this. It's been a very long week. I know the ITER Japan team in Naka, QST, is also working on toroidal rail systems for handling in ITER. Is there any relationship there, and are you working together? Actually, the system is mostly developed by Toshiba Corporation. And we invited Professor Matsuhira in our team, and he was a member of the Toshiba Corporation, who has in charge of developing that systems. So actually, I think there are a lot of knowledge we can learn from them. Of course, there are some different requirements, but I think that is very interesting development, and we'd like to utilize that kind of knowledge.
You mentioned that the work that had been done with the fisheye cameras. Is that published already, or is that? I was interested in finding out more about that research.
Yeah, thank you. We published several papers, so maybe Yamashita Sensei or Komatsu-san. So they are the specialists of this system. So please ask them. So maybe we are very happy to send you the papers.
Is there any question also from the audience online? Okay, then thank you very much.
Okay, thank you very much. So.
Thank you for the nice talk, and thank you also for bringing me in this environment. Thanks a lot. And maybe if you can stay on the stand now, just I promise 5 minutes more. We have the Best Paper Award. So actually there were 3 papers. I mean, all the papers were really nice, so it was really hard to choose one paper. But I'm not sure. Okay, but we first select 3, and from these 3 we have 3 finalists, and we have the Best Paper Award. So maybe Professor Asama can give the award. Professor Asama. Can you come here and give the award? Yes. Wow. Okay, and yeah, I want to congratulate with all the 8 contributions, but the winner is the paper on optimal sensor ranging with UAVs for monitoring of hazardous environment by Andrea Farina, Salwa Amaza, Guy Burgess, and Mirko Kovac. So please, Andrea.
Okay, workshop on robotics for nuclear environments, exploration and decommissioning, challenges and emerging techniques. Best paper award to optimal sensor launching with UAVs for monitoring of hazardous environments, authored by Andre Farinha, Salwa Hamasa, Guy Parween, and Mirko Kovac. Okay, 3rd October 2020, Japan, and Faragasso and Romeo. Okay, congratulations.
Okay, so yeah, I just want to conclude this workshop. I just want to say I hope you learned a lot and you get some idea, and I hope you will networking during the conference and also enjoy Japan. I live in Japan. It's a very it's an amazing country, so please take the opportunity also to go around, and just I hope that more events like this will come in the future. I think as Professor Asama said, this is an important topic, and we have to think that we have to work on this for many years ahead. So I hope we can sensibilize more our community. And also I want to thank my helper here. Without them, this would not work. And I'm also a big thank, I don't know if he's online, to Nicholas. He was really wonderful help. And I want to thank all the speakers and also especially the contributed paper, and wish all a great success in the future. And yeah, thank you very much also to Kaspar, Iain that are still there, and all the people that are online. Okay, so
Thank you very much. Thanks a lot, Angela.
Thank you.
Fantastic workshop. Thanks.
Bye. Okay, enjoy the conference.
Bye-bye.
Yeah, okay.